Hello. Welcome back. Welcome to day two. Thank you for your patience while we work through the last minute schedule changes. I hope you're all able to join us at the reception last night. I got to talk to a number of you and that was great. I have some announcements to start the day out with. First, I'd like to give a special thank you to our gold sponsor, Blue Canyon Technologies, and they provided a short video recap of their company. So please bear with me while help me watch the video here with Blue Canyon.
When you're launching a small satellite mission, whether it's to detect methane emissions, whether it's to gather science from the rest of the universe, or whether it's to detect activities from an adversary, you're looking for heritage, precision, and rapid delivery. Blue Canyon Technologies, we provide end-to-end solutions to our customers. So that's the spacecraft, all of the components. We give them capabilities that enable their missions. Anything from a 3U CubeSat all the way up to an ESPA Grande size vehicle.
Specifically, we provide low jitter, precision pointing accuracy, as well as stable, high-performing GNC systems in dynamic environments.
Part of the reason our customers come to us is our flight heritage. Blue Canyon Technologies has launched over 70 spacecraft, thousands of components, and over 20 different missions. The other differentiator that we have for our products is our products are very highly precise in their ability to point to a target on the Earth or a target into space.
Some of our more recent innovations include a control moment gyro for spacecraft that is enabling agility in the small spacecraft world that has never been seen before.
As Blue Canyon has evolved from being a provider of components to a provider of spacecraft buses, we actually provide a mission operations capabilities to our customers as well, offering services from advanced tests all the way to the full mission operations for our customers. By Blue Canyon Technologies being a wholly owned subsidiary of RTX, we're actually able to leverage the depth of a large company, but the agility of a small company.
Blue Canyon Technologies was founded and still exists to enable missions that otherwise wouldn't be possible because of the price point and the long schedules.
And we're looking forward to giving the next generation of missions access to space.
All right, and if you haven't already been up to talk with them, Blue Canyon does have a booth, so please stop by and chat with them. In addition, we have silver sponsors DHV Technology and Apex, both also have booths, so remember to talk with them during some of the breaks. And our last silver sponsor was Maverick Space Systems. We appreciate all of them. They make this event possible the way we run it. All right, some other logistical announcements. We have posters on the second floor. We'll have some dedicated time to look at them, but I like to remind people it's easy to forget to walk up to the second floor. There's actually a third floor too that has a great view. But the second floor posters, please make your way up there and look at the posters at some point today. We have an up-to-date schedule online. There's a QR code that hopefully you can scan on your name tag, or you can look at the CubeSat DW website to get the up-to-date schedule as we react to sort of everyone's last-minute changes. If you are a presenter, please try to be backstage approximately 1 to 2 presentations before your presentation so that we can make sure the slides are good and get you mic'd up and ready to go. I believe we are trying to send reminders with the phone numbers that you registered for as a presenter. So hopefully you'll get a message saying, oh, you're going to present in a couple, in 10 or 15 minutes, please come backstage. If you don't know how to get backstage, talk to any of the folks with the the light blue lanyards. They can help you find your way backstage. It can be a little bit of a maze the first time or two you walk back here. Okay, so those are the presenters. Tomorrow in the early afternoon, we're going to have a career fair. The career fair is an opportunity for potential employers to talk with college students who are potentially looking for employment or potentially internships. We do need you to register the way the format is set up. We try to, pair small groups of students with a corporate representative. So if you are interested in that, please register. There's a QR code up here that you can scan. There's also a QR code up at the check-in booth inside that you can scan and register as well. So please remember to do that if that's something you're interested in. Okay, with that, it is my pleasure to introduce our first speaker for the day. I'd like to introduce Sophie Fendler. She's going to talk about the WashU satellite, a CubeSat testbed for rapid optical follow-up of gamma ray bursts. Please join me in welcoming Sophie.
Thank you. Hopefully the slides show up. Maybe I pushed the wrong button, guys. I feel like I should start telling jokes, but I don't know any off the top of my head. Ah, we are all the way back. Okay, let me... You got a little preview. Okay, hello everybody. I am Sophie, and I'm going to talk to you about a mission concept called Vector. So I am with the WashU Satellite Group. We are an undergraduate student-led group at WashU whose mission is to design and build real spacecraft. So we were founded about 2 years ago, and we are now about 60 members strong. We are currently working on 2 missions, a 1U CubeSat that will launch next year, and a high-altitude weather balloon mission that will launch this December. But I'm going to talk to you about a very future mission concept that I worked on over the summer called Vector. So from our previous work on a high-altitude weather balloon mission, we came up with an idea for a 3U CubeSat. And so as you do, if you're a university team, the first thing you do is you try to find money. So we submitted a proposal to NASA's CSLI with our idea. Unfortunately, this was not the year to submit anything to NASA. CSLI was indefinitely postponed. But this was a great opportunity for us to look back and reflect on what we had submitted. And we realized shortly after that we had submitted an idea, not a mission concept. We hadn't done any feasibility analysis, we hadn't made any budgets, mostly because we didn't know how. But luckily, we also submitted a proposal to the University Nanosatellites Mission Concept Program. We were accepted into that. So UNP is actually broken into 2 parts. It's more well known for its 3+ year program that helps student university teams take their mission concepts and take them all the way to launch. But after doing this program for many years, they realized a lot of the proposals they were getting were actually ideas, not mission concepts. And so they created a summer-long program for people like us to take our ideas to concept. And so that's what I was a part of over the summer. So me and a couple other interns went to Albuquerque, New Mexico to develop Vector. We actually had a week-long kickoff in Kennedy Space Center where we had a crash course in mission design and everything satellite. So great learning opportunity for all these university teams out here. We also got to tour the VAB, so that's me in front of the Artemis II rocket. Had to throw that in there. So over the summer, essentially we took Vector as a proposal and turned it into a final mission concept. We went through a mission overview presentation, a system concept review, system requirements review, all with NASA and DoD experts. Eventually, in the end, we got to a system requirements spreadsheet, a mission design document, and all of our budget sheets filled out. Of course, this wasn't a linear process. My presentation today will be pretty linear looking, but I want to remind people that, it's 5 steps back, 5 steps forward, 3 steps back when you're making mission concepts. So now to actually get into Vector itself. This is an astrophysics mission, so bear with me, you're gonna have to hear some science. So gamma ray bursts, these extremely energetic events in our universe, they come from supermassive stars going supernova and collapsing into black holes, or neutron stars merging together, so these high energy events. And they produce these jets, if you can see on the left picture, these 2 jets coming out. If we zoom into that, we can see the evolution of the jet. Looking closer at this picture, we notice that it's broken up into 2 phases. We have the prompt emission phase and the afterglow phase. The prompt emission phase happens first, and that's where we see those initial gamma rays. In the afterglow phase, we also get more gamma rays, but we also get light in all different sorts of wavelengths, so you can see visible light here. But after studying these things for so long, astronomers started to notice that actually we get visible light that shows up in this prompt emission phase as well, called prompt optical emission. And this visible light's important because it's actually inside the jet itself. So this is how we can study what the jet is made of, and it's really close to the black hole, so we can study that really well too. So we want to capture that visible light. Notably, it looks like a new point source in the sky, so like a new star or something just appeared. But this actually happens really quickly. This prompt emission phase lasts for seconds to minutes. So if you want to capture this stuff, you have to be fast. So our scientific need is if we have a detector and it captures a gamma ray burst, then we want an optical telescope to capture that visible light within seconds to minutes afterwards. But let's add some more to this problem. Detectors often have a wide, localized region where they know the burst came from. Optical telescopes, on the other hand, often have smaller field of views and have to search through this region to find the burst. For that reason, the development, testing, comparison, and validation of search algorithms for the detection of these transient events is of interest, especially in real orbital environments. Okay, why orbital, you may ask? Well, of course, people have tried to work through this problem before. ROTC was a ground-based observatory that attempted to capture these transient events. However, of the detections that they got, they only managed to capture about a third of them. And even then, their imaging pipeline wasn't great, mostly because of weather and their location on the Earth. So we thought, why don't we put this on a CubeSat? So, just to recap, we want to capture these prompt optical parts of gamma ray bursts. To do this, we have to perform searches very quickly. Doing this in space can be faster, better, potentially cheaper. But first, we actually need to figure out if searching for transients is even viable to do on a CubeSat. And catching these real bursts is hard. We don't actually want to depend on that for a technology demonstration. And for that reason, we want to figure out a way to, have our search be reliable every time. So we decided to figure out a way to make an artificial transient. In order to do that, we figure out the regions that Vector will see when it's in space. We then make a copy of that region on the ground, and then we remove a star from one of those copies. We now have an altered region star map, so if Vector looks at this place in the sky, it's going to see a new point source that appeared, just as if a transient had suddenly popped into existence. So from there, we defined our mission. So on a CubeSat form factor, we want to demonstrate an optical telescope with onboard processing to perform search algorithms. So we're capturing astronomical images and using onboard processing to detect transients. So we came up with two experiments. Our minimum experiment, just to test this out, is to test out comparison algorithms. So again, we have that altered region star map that we're now going to load onto Vector on the ground. And we can put as many of these as we want on Vector. Well, as many as our data can handle. And then we get into orbit, and we tell Vector to look at some place in the sky. And Vector determines when it will see that location and store that information. And then at the time of observation, it will slew into position, and it will actually take a picture. And then it will run a basic comparison algorithm on board to try to see if it can find the missing star. To actually take this one step further, we decided, we want to actually be able to search a larger region as if we were looking for a burst. And so here's our full experiment where we have a larger region that we search through until we find a star. Yay, we found it. Okay. So then after this, we did a lot of feasibility analysis over the summer. To do that, first we had to pick out some preliminary components. So our payload is a COTS Canon lens and a scientific-grade CMOS sensor, as well as a Raspberry Pi. And then for our ADCS system, we used their ClydeSpace ADCS a GPS, and a sun sensor. And then we chose an S-band patch antenna for our comms. And as you can see, we went from a 3U to a 6U very quickly to fit all of these components. So this is our volume budget, all laid out in a 6U. For our pointing budget was also a very big concern because we want to be able to pretty accurately point at these things. So we had a 2 arc-minute pointing requirement for our mission, and taking into account all of our errors from our ADCS, our positional knowledge, mechanical alignment, and thermal error, we were within that 2 arc-minute requirement. As for our torque and momentum, we have a max slew rate of about 1 degree per second using this ADCS system. We also did a power budget by first breaking Vector into different modes. Notably on this, I wanted to put this up because we do experiment in Eclipse. For that reason, there's thermal concern from our sensor getting too hot if we were not in Eclipse. And the sky is darker in Eclipse naturally. And so we could be able to see things to a greater limiting magnitude. But looking at our energy balance over time, doing both experiments, we never get below the watt hours that would be detrimental to our batteries. We also did some basic simulation work to actually simulate the images that we would see on board. So by putting in all the specs of our sensor and imager, we could figure out actually what images would be outputted to what limiting magnitude. So in conclusion, the future of Vector, what does that look like? As I said, we have 2 other projects. So our 1U is to build flight heritage at WashU. It's also got a pretty cool controls payload on board that my colleague Jesse will be talking about tomorrow. And ARIS is our high-altitude weather balloon mission, which is trying to detect these optical counterparts of gamma ray bursts. So this gives us optics experience and helps us develop the science. Combining these 2 missions together is how we get to Vector. And so we do plan to eventually submit a proposal to this longer 3+ year program and take our concept that we developed over the summer all the way to launch. So with that, I'd like to thank you and see if anyone has questions. Also happy to talk about the mission concept program if you have questions about that too. Thank you.
So you said that the gamma ray bursts are associated with some light burst, yeah?
Yes.
What's the delay between the 2, the latency between the 2?
Yes, good question. So the gamma rays are detected instantly. And we've never caught optical with the gamma rays because no instrument has ever turned at the same time. But we assume that they happen pretty simultaneously. So as soon as gamma rays appear, then optical light should be there too. And then that optical light, that afterglow lasts for hours. So you can see optical counterparts for a long time, but they get dimmer and dimmer over time. So we made an artificial transient so that we don't actually have to watch any certain area and try to capture a real burst. But the way we'd pick our spots is determined on what magnitude of stars we want to see.
Maybe a third. So would it help you if you would have a gamma ray detector which can sense which directions the burst is coming, the gamma ray is coming, and then you...
Totally. Unfortunately, gamma ray detectors are giant and would not fit on a CubeSat. But there is a telescope, a giant gamma ray burst telescope called SWIFT that has both a gamma ray detector and an optical instrument on board. However, it's so giant that it takes it a really long time to move its optical telescope into position to actually see the burst after the gamma ray detector detects it.
The reason they are big is because it's very low energy, I mean, very low flux into gamma rays, or?
I would assume so. I can't answer that completely, but yes.
Thank you.
So, kind of as I was explaining before, we're not actually going to try to catch real gamma ray bursts. Sorry, I have to cough. We're not going to try to catch real gamma ray bursts. Instead, we've made a way so that we look at artificial stars, that artificial star map that we've removed. Now, in future projects, whenever a gamma ray burst detector detects a burst, they send it to something called NASA's General Coordinates Network. And if we are locked into that, then we can know where to look. Mm-hmm. Yeah.
If do gamma ray bursts tend to repeat, or are they just totally random?
They are totally random, because a black hole probably doesn't make bursts twice. The star collapses once, makes the gamma rays. Yeah, they're not like the fast radio bursts that you get those repeaters, which is really easy to go and look in that position. Yeah, so it's random in the sky. Yeah. Anything else? Okay, thank you guys. Do I know this? Yeah, thank you.
Next up, please join me in welcoming Adrit Sinha, Dhruvil Patel, and Effa Anais Kanu from Oakwood School.
Good morning, everyone. Today we'll be telling you a little bit about our acoustic sensing payload. So we're NeonSat, a CubeSat team from the San Francisco Bay Area, completely high school student-led, built, and designed. We were selected in 2024 as part of CSLI's Call 15, and we're anticipating flight in early 2027. Our primary mission spans over 45 days, and we're hoping for a year of usable on-orbit data. We have 7 payloads, 4 of which are technology demonstration, and today we'll be telling you a little bit about our acoustic spacecraft mapping and sounding payload.
All right, so our payload performs system identification. What we're going to do is that we're going to excite the structure, and then from there, listen to the response over time. This is going to allow us to learn about the dynamics and if key elements have deployed. System identification has been used for a long time in spacecraft design and testing. In the early 1980s, NASA for the Galileo spacecraft performed system identification. This was also an early use of the eigensystem realization algorithm. So what NASA wanted to learn is if their spacecraft would survive launch, and also about the structural dynamics of how that would affect control. So what the engineers did is that they excited the structure, and then from there, listened to the response over time. All right, so but why perform system identification? Basically, it tells you about the structural dynamics of the system. In other words, how it naturally likes to move. When we measure the structural response, we're going to be able to infer information about our structural dynamics and if key elements have deployed. What NeonSat is going to be doing this year, however, is that we're going to be doing this explicitly in space and as an ongoing diagnostic. All right, so let's see how we're going to actually do this. Here's an overview of our payload. We're going to have 1 solenoid and 2 mic boards. Our solenoid is going to excite the structure, causing waves to scatter, reflect, and damp out. And then our mic boards, using the piezoelectric effect, is going to convert the relative displacements into voltage, which we then record. Here's our solenoid. Our solenoid is a non-magnetic stainless steel tube. Around it, we wrap around a coil magnet wire, and then inside is a permanent magnet. This produces an excitation roughly equivalent to a 50 microsecond 40 Newton half-sine tap. And in the bottom of our structure, we have a lot of space, so we opted for a simple solenoid design instead of optimizing for something like mass or volume. Here's our mic board. Our mic board holds our piezoelectric sensor, which just measures the vibrations in our structure. Our design includes a frustum. What a frustum allows us to do is that there's a consistent contact patch for sensing off of, and our design also includes spring mounting. What spring mounting achieves is three things. First of all, it allows us to measure, there's this consistent force applied to the structure. The mic board itself is going to be isolated from the movement of the structure, and also it allows us to tolerate manufacturing variation really well. One last thing is that this idea for applying springs came from how CPU mounts, how in some CPU mounts there are springs attached on the fastener stack. Here is a timeline of our excitation sequence. We're going to tell the satellite to perform an excitation sequence. From there, our OBC is going to trigger our CPB micro to tell it to, hey, retract and release the solenoid. This is going to produce an excitation, which we then read from our piezoelectric sensors. Our sample rate is about 250 kilohertz, and this is going to be read through the two mic boards as ADC channels. This will produce 9K samples, or about 37 milliseconds of data, but the first 6 milliseconds of active response is sufficient to resolve key modes. Our data is then going to be handed off to our OBC, and our OBC is going to downlink the data to us, and then we're going to send a command to the OBC to discard of the information.
So this is our plan for life in space. So we'll tap the first time before our Z plus solar panel, deployable solar panel deploys, and again after. And once we receive those readings, we'll be able to accurately tell if it has effectively deployed or not. And then our long-term structural monitoring includes weekly tests for structural integrity to see fasteners loosening and just see how life in space has affected our spacecraft. So we began experimenting this in 2024 with our first test was an aluminum beam with a hinge and a solar panel attached that acted as our deployable solar panel and our structure. And with that, we were able to test stowed and deployed configurations, and we captured that on our in-lab oscilloscope using sonar. And from that, we applied autocorrelation to identify the wave propagation and see the reflections. So here are our first measurements from that test. You can see the top one is the stowed configuration, and the bottom one is the deployed configuration. So the first red line corresponds to the end of the structure itself, the end of that aluminum beam. And the second red line is the aluminum beam plus the deployable solar panel that we added. And from this, we were able to see two things. So first, we were able to see how changes in structure affect how waves travel in the piece of metal. And also, we were able to get a kind of accurate representation of how this will look in space when our deployable has deployed and what we should be expecting.
So this past year, we've made significant progress. This is our flat bar experiment, which integrates our flight hardware that we intend to fly on NeonSat. So we have our solenoid and our mic board mounted to a flat aluminum bar, and we have holes for adding mass to detune the bar and to suspend the bar in the air. The reason we suspend the bar in the air is to allow it to freely ring. Our mic board and our solenoid are both hooked up to our combined payload board, which is in our flat sat. And our CPB uses versatile analog and high power I/O to control these kind of payloads. So we made a simple model of our structure and ran dynamic FEA and calculus to predict how it moves. So this is a picture of our dynamic modeling in calculus. So we virtually excited the structure with a half-sine 50 microsecond tap, and then projected the displacement under the mic board. So note, note that this is a very simplified version of the real geometry in our flat bar experiment. These are our predicted responses. So the bottom graph displays how the structure would be predicted to move at the probe point. So this is our actual measured time series from the experiment, and we're pleased to see that it looks fairly similar to the predictions that we took from calculus. The sensor is connected to our CPB, and it's sampled at 125 kilohertz. The solenoid is slightly sharper than we modeled, and at the beginning, the signal is slightly higher, which results in it being very close to clipping. And also, we've seen that it's highly repeatable, as the traces are visually identical in between runs. And we've also found that even adding a small amount of mass changes the waveform highly. So that suggests that it's pretty sensitive to any structural changes. So previously, we looked at responses in the time domain. So similar to sonar, this tells us how long the waves take to reflect. But frequency domain, on the other hand, frequency domain analysis, it lets us find the structure's resonant modes. So if something moves or changes in the spacecraft, the peaks of the graph will shift. And so this is our table, which compares the modes that we took from the flat bar experiment using ERA with the modes we found from FEA. And the good news is that the modes are fairly similar between the two. So we know that it's pretty accurate. But it does seem that we have less sensitivity to the lower frequency modes. But we think this variation could be due to inconsistencies in our model and testing apparatus. So why did we do this? We originally developed the payload to determine deployment states for our own smallsat, but we're also excited to use NeonSat to study actual spacecraft dynamics and structural aging in smallsats. And we are highly excited to be able to use it in more complex missions in the future. So going forward, we want to focus more on testing, which includes vacuum and end-to-end radio testing. But we also want to start on the manufacturing process, which includes machining and coil fabrication. So this is a picture of our in-house coil winding machine. This is what we use to wind our solenoids and our magnetorquers. And we are planning a complete end-to-end software integration test, but we can already command our spacecraft and receive telemetry data. But next, we want to integrate a high transfer of bulk acoustic data as well.
All right, so let's look at some pictures of how our payload fits into our structure. You can see here that it's positioned at the bottom, and also here you can see like how big the actual solenoid is. It's like what, 2/3 of the structure's length. Here's another picture to better see the contact geometry, and here you can see the two opposing mic boards. All right, so far we've looked at predicted and real responses from our flat bar test. So let's look at some predicted results of our actual structure. Here's a predicted time series from our dynamic FEA at both of our probe points. These are the two mic boards. And applying ERA to that recovers like the key modes that we've seen in other analyses that we've done with things like NASTRAN, ANSYS Workbench, or Calculus. We believe system identification in space will really allow us to understand Nyansat's dynamics better, and we hope that this will be useful in future missions. Thank you for listening, and we'd love to take some questions. Yeah. Sorry, could you repeat that? I'm not exactly sure, sorry.
So most of our analysis was done by our instructor. We kind of just ran experiments and research on it. But if you could see us after, we would love to take your question. Thank you.
Yeah. Yeah, so we're planning for a year in orbit, and from that, we're going to be taking our like weekly excitations, and at the start, we're going to do more to see if things have deployed. And to get it down to the Earth, we're just going to be downlinking it from our OBC all the way to our ground. Does that answer your question? Oh yeah, our sample rate's 250 kilohertz. No, so due to our RAM limits, we only get 9K samples. That's 37 milliseconds of data. And the first 6 milliseconds, however, are just enough to solve for our actual key modes. So I don't think it's going to be in like the megabytes or anything.
Yes.
Why not compute everything on the CubeSat itself?
So it takes a lot of resources, and we don't have that on our CubeSat.
It also takes like a lot of space, so we kind of just want to downlink it to our ground station. Yes.
S- so we are going to take some graphs when we are down on Earth, and then we can use things like autocorrelation to compare that from the graphs that we get from our satellite. So to see the difference between whether like the structure is cracked or like one of our solar panels is going to deploy. So to see if the difference between that, we're probably just going to use autocorrelation. Does that kind of answer your question?
Uh, yeah, I'd love to take your question after. Yes. Yeah, a couple of our next steps is vacuum testing. So we will see if that does affect like our waveform or changes in our structure.
Yeah.
Wait, sorry, could you repeat that?
The rest of our satellite is pretty packed. At the very top, we have another payload, and then we have our board stack, and then in the middle, we have our batteries and our magnetorquers. So there was really only space on the bottom to like fit them. So that's why we put them there.
Well, actually, none of us are a part of the software team, but we'd love to take your question after with the rest of our team. And yeah, but please see us after. Thank you.
Thank you, guys.
Thank you.
Next up, we have advances in CubeSat-based active and passive remote sensing and Earth observation by Naresh Dio from Visionary Solutions.
Good morning. So today, I would like to talk to you about advances that have been made in the last 10 years or so in remote sensing and Earth observation, but primarily using CubeSats or small sats. So idea of the presentation is to show how it's possible today and going forward to make major observations and major remote and complicated remote sensing just using CubeSats or small sats. So my presentation would first talk about the motivation and what are the drivers for using CubeSats for Earth observation and remote sensing. And then I'll talk about some of the applications and objectives of remote sensing, what is possible to do with remote sensing, and discuss a few of the active and passive instruments or equipment that is used for it. But most importantly, my discussion will focus on what are the factors, what has happened in the last 10 years or so that makes CubeSat-based remote sensing and Earth observation possible, and how much, what needs to be done next. I'll give examples of a couple of recent developments or deployments as well, and then what are the trends and future possibilities for remote sensing. So we will address primarily focus on things that are new or advances during the last 10 years. And largely, the emphasis will be placed on Earth observation and measurement of geophysical parameters that are of significance. Even though many of these instruments can be used for planetary or other Earth-based observations. And because of shortness of time, I will limit the presentation to radio frequency, microwaves, millimeter waves, and terahertz-based observations and instruments. And just for purpose of clarifying, I have given the frequency ranges for millimeter waves and terahertz. These are very rough. I used decades as a way of making delineation, though there would be some difference of opinion on where this demarcations take place. So once again, talking about what is driving this move, or what I'm proposing is driving this move, is the privatization of space. So, and that's pretty obvious, I don't need to explain it, but data as a means of conducting a business is also very important in the recent times. There are serious reductions in the barrier and mission cost, and obviously the development time, as you are all aware of in case of CubeSats. Then there are technological developments in remote sensing that have taken place in the last 10 years that seriously contribute to the viability and of CubeSats-based remote sensing. Previously, it took something of the size of a refrigerator or even a school bus to do Earth observations, and today it's possible from 2U, 16U type CubeSats. And that obviously is an important factor. And then the availability of infrastructure, both in space and on ground, that facilitates use of smaller satellites and constellation of satellites for observation. So ultimate objective of this presentation is to strongly promote and facilitate through this growth CubeSat-based observations, and hopefully some of you or many of you will consider using some of the instruments that are available today for Earth observation. And again, this is a huge list of all the applications, and this is by no means a complete list that can be done from low Earth orbit or even other orbits as well. Critical parameters, they deal with climate and weather as well as with other features of our planet, such as oceans and salinity and water, surface water. And you can see that there are other sort of research and technical observations which will lead to future instruments. And monitoring of species like ozone, chlorine monoxide, methane, and other trace gases for helping. And in some cases, is for surveillance purpose, these CubeSat-based instruments, or for understanding compliance or for enforcing compliance and accountability for businesses and industry and even governments for that matter. So very briefly, the instruments that are commonly used, and I'm sure people are coming up with even more complicated instruments. In passive, there are radiometers, imagers, sounders for temperature sounding, and spectrometers. And in active, of course, we are familiar with different types of radars and interferometers or reflectometers. And of course, signals of opportunity are always a good way to do remote sensing or monitoring of various Earth-based geophysical features. So finally, the real purpose of this presentation is to talk about those key factors, those things that contribute to the feasibility and in some cases the swap reduction of the instruments and other peripherals that allow you to do remote sensing using relatively small CubeSats in the range of 2U to 16U or small sets for that purpose. First factor is itself in the advancement in these instruments, techniques of making various observations or measurements. As we talked about, some are optical, some are microwave, some are infrared, but today's focus will be on RF and millimeter waves mostly. Semiconductor technology obviously has evolved greatly in the last 10 years. And then things like AM or additive manufacturing. I will also spend quite a bit of time on antennas because obviously when the satellite is small, its aperture is limited in the past, but advances in antenna technology in the last 10 years or so have made it possible to do relatively sophisticated remote sensing or Earth observations using microwaves or RF techniques compared to what was possible before. So those, I will also spend some time on that. Of course, digital beamforming and scanning and so on techniques have also allowed us to make more sophisticated measurements. Of course, high data rate radios and other software-defined radios facilitate the transfer of such data from the instrument to Earth-based stations. Then there are some possibilities of using large constellations of satellites because of, again, reduction in cost and barriers to entry. So you can do a global coverage and also have time-based coverage of Earth from many of these instruments. And finally, as I discussed before, the infrastructure that has evolved, services that have become available now, make it easy to make really solid observations and get the data back to Earth. So I will not focus on actual numbers, what is the reduction in size of these satellites or instruments doing comparable science and comparable measurement activity, but it is much more than tenfold. Same goes for the cost and the swap of within CubeSat community, what has happened to use of these instruments, how much smaller and better and lower cost they have in the CubeSat itself comparison. So talk about semiconductor device technology. There are advances in power amplifiers and transmitter technology, either using gallium nitride, which is a great way to make high power transmitters. We will talk about it momentarily, or silicon-based devices, CMOS, silicon germanium, and so on. And then there is the evolution of surface mountable devices, which of course help in reducing the form factor and the size of your payload or instrument. And beamforming, which we discussed yesterday in another presentation, and scanning and so on, allow you to do much more sophisticated work or coverage on Earth. And there are also development of ultra-low noise receivers. So for instruments that are doing observation using passive techniques, that is very significant and useful. I have spoken about gallium nitride many times at this conference before, but it certainly is a game changer when it comes to producing fairly large amount of power in a relatively small size or with a good swap C. Gallium nitride can operate at pretty high junction temperatures, so it's possible to pump a lot of power in your transmitters, particularly helpful for radars or SARs, the synthetic aperture radars. That's typically a great boon to them. And you can have efficiency of 20 to 50% using gallium nitride, depending on the frequency of your instrument or transmitter. Then the surface mountable devices, as opposed to huge three-dimensional devices, it's having things which are conformal and make sophisticated circuits. That is a new thing. And AESA, or the active electronically scanned arrays, are certainly a big help in both SARs and other radar-based instruments. Then, of course, as I discussed earlier, the silicon-based technologies, which are CMOS, SiGe, and HBT and other devices, which were previously not at all capable, now they have integrated circuits that just a single chip or single device can be used for fairly sophisticated activities or sophisticated functions, as the case may be. Then, of course, as is the case always with CubeSat, the CATS devices which are available, and the philosophy of using CATS devices for making instruments for CubeSat is a big help. Yesterday we had a paper, we had a presentation on AM, or additive manufacturing based heat pipes or oscillating heat pipes, but there are many other technologies, both in surface heat transfer layers or interface layers and so on, or choice of materials for substrates that help in removal of heat, which is one of the biggest problems in any satellite, particularly small CubeSats, how to remove heat from such power generating or such heat generating instruments. So again, in the interest of time, I will not speak on a subject which is in itself a whole seminar or presentation on additive manufacturing's use for making microwave and millimeter wave or RF componentry, which of course has a big impact on your size, weight, and certainly on cost, because it removes a lot of unnecessary bolts, nuts, and screws. So here are examples of some of the parts. Particularly in optics, is really helpful to use additive manufacturing. So you see some antennas here in this picture, some lenses, and of course the second from left is a oscillating heat pipe that was presented yesterday. It's an earlier version of that, that oscillating heat pipe using additive manufacturing, and of course lenses and waveguides. So all these, when you add all these different factors together, is what leads to a remarkably lower swap and remarkably more affordable and, equally importantly, powerful instrument that can do real science and measurements that were possible only from huge satellites, which took dozens of years to create and close to $1 billion to deploy. Now, I will talk in the balance of my talk about antennas, because antennas are really key to observation, whether it's passive observation or Earth-based observation. So there has been a lot done in antenna technologies in the past. So I'll give examples of some previously launched instruments. This is RAINCube, which stands for radar in a CubeSat. And this is a 6U. And you can see a fairly large antenna deployed for doing the Ka-band radar work. Ka-band in this case is 35.5 gigahertz. And here are some other examples, real examples of real CubeSats that have been used. Some 6U, and Marco is the one that was a pair of those two, Marco 1 and Marco 2, went all the way to Mars and were used in the data transfer from larger Inspire and other payloads to Earth. So again, I will only just breeze through these past accomplishments of commercial art, of pretty large antennas that can be deployed from a relatively small 2, 3, 6U CubeSats. Here are some other concepts which have not been used yet, but I'm proposing them to make compact, relatively compact antennas for CubeSat use for doing Earth observation. A few more examples of such antennas or products. This, again, we discussed with some of you the use of gap wave technology or band gap technology for making flat surface antennas that would normally be a parabolic dish or a large substrate. So finally, I would talk about some of the instruments in the last 10 years that have been deployed and have very successful data transfer to Earth and led to development of other instruments as well in the future. So they do different remote sensing. HIMSS was deployed in January and is sending incredible data by hyperspectral microwave on moisture and weather and other parameters that we talked about. And here are some references. And again, if you wish to learn more about it, or now after this presentation are excited to develop a, develop a instrument or a payload or a mission for remote sensing of our planet, then I would certainly be available to discuss that. And here is my email address. Thank you. I have time for a few questions or observations or comments or corrections to what I said. Yes, sir.
I'll just ask, on all those advanced antenna concepts, how many of those are commercially available? Like a lot of those look like kind of custom solutions.
Well, a lot of them are published, so you could get them made. But for example, there are companies either here, there are some companies here, for example, CubeSpace, or that have commercially available antennas. And then there are, so to answer your question, there are quite a few companies that make antennas similar to that. There are some with very kind of amazing concepts of deploying antennas. I didn't talk about them, that are wrapped around and then they go. So yeah, the many are available, but company like Gapwave, those antennas are commercial. So yet, you may have a need for 2-meter antenna, and you may have to go to a house to get it custom made for you. But none of them are esoteric in nature, and they are only a physics concept. They're all real. That answer your question? Sorry, I should repeat the question. How many of those antennas are commercially available to a CubeSat mission planner who may not be directly an antenna person, but maybe a person whose interest is in some other aspect of their payload? So antenna is sort of a necessary evil for remote sensing or Earth observation. Any other questions, comments, observations? Okay, I have 3 questions, so I'll start with you.
What phenomena do you have in mind for terahertz imaging from space?
Most of the observation in terahertz are of significant molecules, such as water vapor. And terahertz in this case is frequencies in the 200 to 400 gigahertz range. So terahertz, even though terahertz implies 1,000 gigahertz, in that range, because beyond that, you are really dealing with infrared or sub-millimeter wave observations. They're generally passive observations of significant molecules in Earth's atmosphere, generally water vapor and so on. So you can map them, and again, if you are interested, I can give you some specific examples of instruments that are. Tempest is an instrument that was mentioned there, developed by MIT Lincoln Lab, that uses sub-millimeter waves for weather and climate work.
Thank you.
There's a question here and one behind there.
Yes, as part of your research, have you built a database of applications that could be consulted?
There is actually not my own research, but there is sufficient amount of references available on what has been done or what can be done. Database, there are a couple of databases available. I think one of my references here is not giving you the actual site. The ESA Living Planet Symposium and so on have databases of what can be done. What has been done or what can be done is more important. There was another question in the back there. All right, well, thank you very much. And let me say this, let's give a round of applause to all the volunteers who have made this possible in a seamless and such professional manner. So let's give it up for all the volunteers who made this symposium possible. Thank you.
Next up, please join me in welcoming Cannon Kilcrease from Oklahoma State University. He will be presenting a presentation on a low-cost 1U CubeSat form factor platform for near-space testing and education. Thank you.
Hello, my name is Cannon Kilcrease. Like she said, I'm from Oklahoma State University, and today I'll be presenting about our 1U CubeSat how-to balloon platform. I just like to say it's definitely going to be a change of gears, kind of into more educational program, but I think it will be nice information for new and upcoming CubeSat programs. So I'd like to start out with a summary. I'm going to start with the background, kind of what our CubeSat program is, and then talk about the motivation for this project, and go into the mission a little bit, and then go into the design, and then at the end I'll end with some acknowledgements. So start out with the OKSat team. Here on the left we have the undergraduate team. There's about 7 or 8 students of us at a time, about each semester, and in the back you can see our ground station. That's what they've been focusing on the most for the past year or so. And then in the middle you can see our senior design team for this year, They are actually developing the 3U CubeSat mission that we're working on. And then over on the right is some faculty, John O'Hare and Aman Farouk, that are our PIs. And then kind of I talk about a timeline just to show that where we're at in the program and why we're doing this. So in 2020, we got a grant from NASA to do like an RF optical communication type thing. And in the same year, initially that wasn't a CubeSat mission, but in 2020, that same year, they wanted to start a CubeSat program in Oklahoma State. So they went ahead and did that with some extra funding and help from OAIR. And in 2023, a senior design team started working on a ground station, and that was kind of the first push to get into like the CubeSat program. And they worked on that for a few years. And in 2025 was our first senior design team to start developing our 3U CubeSat design. And then we worked on that over the spring and over the summer. We got our proposal ready for CSLI, but CSLI got pushed back and things kind of went to a halt, so we didn't end up getting to go through with that. But this year we got selected for the UNP program, the University of AMSAT program, so we'll be doing that this summer. And and then the next goal is to try to get into the CSLI program and make this launch happen. So I just want to talk about some of the motivation behind my project. Basically, as you can see, a lot of the work has been done by the senior design team, and this is great in reality, but you know, there's pros and there's cons to it. I mean, seniors are going to have a strong fundamental engineering skills. They're also going to be motivated to perform well because they need to graduate, need to do good on this project to graduate, and they also had to sign up for this program, so they have a willingness to learn about CubeSats and a willingness to work hard. But at the same time, they do have limited experience with CubeSats. Most of the students are CS or EE majors, which they don't know much about space missions, which most of the time is spent learning about how CubeSats work, how space missions work, and you know, in one semester, it's hard to get a lot of work done. And in theory, it would be nice to incorporate undergrads into the program, but with an up-and-coming program, a smaller program with less experience, limited funding, and limited resources, it's hard to find time or the resources to incorporate undergrads into the program. And that's kind of something that I've realized being a second, it creates a bottleneck in our program. So a solution to this is we're trying to develop a low-cost CubeSat mission. I'm going to call it a balloon sat for short, and to minimize financial risk and to enable hands-on learning in an environment that you don't have to worry about risking, expensive parts, expensive components, and you can just go in and start working through gain practical skills and do testing, iteration, and system integration just like you would in a normal CubeSat. And this also will familiarize the younger students with the 3U CubeSat program, so when they do end up getting into the senior design team, they will be ready to start off and just get to work. And you can kind of see my idea for the pipeline here is break off the student organizations working on the ground station for the mission, but then also working on the 1U CubeSat, balloon sat, and then that will create a pipeline into the senior design teams where they can directly start designing and building our 3U mission. So here's a mission statement. Just to kind of have a goal for us to shoot towards. Basically, the idea is to construct a 1U CubeSat form factor system that replicates the core systems of a traditional CubeSat while operating in a near space environment. And then at the same time, since we are coming to an end in our ground station work and we're wrapping things up, I want this to also incorporate, or to be a kind of validation and testing for the ground station infrastructure. And then some secondary missions. Like I said, we're trying to make this into a framework so this can be followed by future students, and they can have an easy access pipeline into the senior design team and to learn about CubeSats. So we're just going to have to be well documented, structured, and a low cost introduction to CubeSats and the pipeline. And then also we're looking to do some type of secondary, experimental payload besides just the ground station validation. So we're talking with faculty at school and trying to find some, maybe sensors or other things we can include in our mission. So here is the system architecture for the 3U. This is a blown up CAD model of the 3U mission that we've been working on. And the reason I'm putting this up here is I just trying to show what it looks like and the diagram of all the components and how they're connected. And then on the next slide, I'll show how our balloon sat is compared to this. So this on the left, that's the Artemis CubeSat that we got a few years ago, and basically this is the inspiration of what we're trying to make our balloon sat look identical to this. And then on the right is kind of a flow chart of all the components we'll be using, just like the diagram on the last slide with the 3D CubeSat. And I'm basically just trying to show that we're trying to make this very similar to what the 3D mission is like. And then talk more about the hardware. We're using non-space grade commercial, like off-the-shelf components. On the next slide, I'll go into more talk about what those are and then how they're compared to each of the components we have picked out for the 3U. But the reason we're doing this is to obviously reduce cost and lead time. We can buy multiple of these components, and we don't have to worry about breaking them because they're not too expensive, available, easy replacement, and also just pressure, hands-free development for these younger freshman, sophomore, junior level students. So, and then more on the kind of the hardware, I'm a double E, so I enjoy the communications, and I kind of just wanted this slide to show that we have our transceiver for the 3U CubeSat, and I'm just kind of listing some specs for it and how we're going to match those with the one that we're going to use on the balloon sat is the Hack RF. I'm sure some of y'all may have heard of that. And then over here to the right, we have our link budget, just kind of showing that it's going to be a similar environment to in space, but it's not going to be identical. The altitude's going to be the main thing. And then more of the hardware, basically. Up top, you start with the onboard computer. So for the 3U CubeSat, we're using mainly GOM-space components, but as you can see for the OBC, instead of using the GOM-space part, we're just going to use like a Raspberry Pi, which is readily available. And then for like the docking board and stuff, we're going to try to create some custom PCBs to interface all these components together. And then we also have like custom antennas that we can make very cheap, just out of copper, like monopole antennas, and then GPS systems are just cheap camera modules, batteries, battery pack, power supply, and the chassis will just be 3D printed, or we might even mill it out of aluminum. And then kind of go into the balloon, like the mission operation, since this is going to be a balloon mission per se. It is going to be a lot different than a normal CubeSat mission. And a lot of things kind of need to be accounted for and ready to experience. So basically, there will be a balloon, it'll be filled with helium, and the 1U CubeSat will be attached to the balloon. And then we will fill it up with helium, launch it. It takes about 2 hours to get to the apogee. That's about 20 kilometers, and then it will float at around the 20 to like 22 kilometer range for 9 hours. The wind is going to be the biggest. It's going to be all driven by the wind. So we have an estimate of where it will be going and where it will land, but it's all rough estimates. And then once it pops, per se, it will take about an hour to all the way down to recover it. So, and the biggest problem with this is when we're trying to do tracking with our ground stations, we need to know where this is going to be. So we will have a GPS on board, and we will have to have some type of handheld antenna so we can get a GPS ping and know where this is at, and then we can start tracking with the ground station. And then to validate our communications, we're basically just going to send a transmission to the satellite, receive it, and then it's going to transmit that signal right back down. And then we'll look at the quality and analyze the transmission and see how that works. And then if that goes well, we will, on the 3U mission, a big part of it is we're going to have an optical system, a camera, so we're wanting to incorporate a camera on this 1U model, and if the first communication test goes well, then we'll end up taking a picture and transmitting that back down and reconstructing the image and seeing how that looks. And we're going to try to replicate, the window of time you would have for a normal pass of a CubeSat. So we're estimating like 5 or 6 minutes, and try to transmit that data back down in that window. And then kind of to wrap things up, just want to talk about like the educational framework and documentation for this. We're following the Space Mission Analysis and Design book pretty heavily, and like me and then the other few students that are working on this, we're relatively new to CubeSat, and we're using this book to kind of guide us through the steps and the process of doing all this. But basically, we're trying to make a framework that is transferable to younger students, but also even to other schools, like high schools or other CubeSat programs that are just getting into space. And, hands-on and iterative improvement as the years go on, we can tweak this and make this better and make this kind of we can give this project to new students, and it'd be like an onboarding process for them to get used to CubeSats and to work up into the senior design team. And then acknowledgements. I'd just like to thank Dr. Farouk and Dr. O'Hara for their support, and then Jack, or Mr. Graham, he's gave us a lot of money donated a lot of money to our program to get us up and running. And then also I'd like to thank Oklahoma Aerospace Institute for Research and Education, OAIR, and they have a how-to balloon team. They will be providing the balloon itself, and then we'll be attaching our payload to it. And we couldn't do this without them. And they will go through help us with the mission operations of the flight and tracking the balloon, and they've done this before, so we couldn't do it without them. And that's all I have. Thank you. Any questions?
During those 12 hours, how far downrange is traveling the balloon?
It can be a good distance. Ultimately it depends on the wind. So it's just a lot of making sure the wind speeds are good, and I'm not too sure on that because we're relying on OAIR to kind of help us along with that. But I don't think it should be more than 10 kilometers or so. But yeah, I'm not too positive. But
Curious, as a new university lab, like what have been the biggest challenges for you to get your program started?
So he asked what were the biggest challenges to get our program started. I would say first, the biggest problem at first was just the information from semester to semester. Like I said, we had the senior design teams working on it, and at first we just kind of didn't think of documentation. And obviously we had a lot of data and a lot of designs and stuff, but it would just get lost. And so we have this last year been trying to do a very, very good job of making sure everything's organized, and then having a good send-off kind of transition between groups. And any more problems? The reason why I'm doing this is because I would love to work on, if we could just pump out CubeSats, that would be amazing, and actually get this in. But it's hard when you're limited funding. So that's the reason why I had inspiration to do this is, if you feel like you're building a CubeSat, you're not just, it doesn't feel like you're just doing meaningless work. But and it gives you a good experience. So. Yes. Yes. When I was showing this to the PI, Dr. O'Hara, he was like, you know what, we've actually been talking between him, he's an electrical engineering professor, and then 2 mechanical aerospace professors, and they're actually thinking about having a class. So instead of like a senior design, just like strictly design, they would, 1 month or maybe 3 weeks, one professor would teach about communications and like the avionics, and then the next week they would talk about something else. And yes, that has been a thought, and that would be something ideally we would like to do. So yes, that'd be awesome. Good.
Have you thought about having a sort of a sub-team on this that looks at the mission flight, like how fast do you ascend? Do you target a specific layer of the atmosphere to get a certain wind speed?
Yeah.
Essentially, how do you fly the thing?
Yeah. So his question was, have you thought about making a sub-team for the actual flight? We have, and Aware, they have a team that does kind of the how-to balloons quite a bit, and we're working closely with them on a lot of this. So I think that I'm relying on them for a lot of that. And when it comes to the day that we actually do it, yeah, I mean, at that point, I'd hope we have a good idea, but they'll definitely be there to help us out and any of those questions. So. Yeah. So I mean, one thing. So we're building this, and it's the frame's either gonna be plastic or aluminum, but we all do have to put this in a styrofoam box. So just in case something it comes down and lands on somebody's house or car, it's not gonna damage it. So yeah. But I think that's all the time I have. But thank you.
Next up, we have Drew Glassbrenner from AMSAT presenting on 2026 AMSAT updates.
Hey, good morning. I understand I'm the last thing between you and lunch, so we'll try to make this quick. I appreciate the opportunity, kind of a drop-in presentation here. Wanted to introduce everybody here to AMSAT for those who don't know who we are and tell you what we've been up to the last couple of years. Okay, there we go. Clicker's not working. Hey, backstage, the clicker out here. There we go. Thank you. Maybe I wasn't pressing it hard enough. Forgive me if I turn around. I wrote these slides this morning. The Radio Amateur Satellite Corporation, we formed in the District of Columbia in 1969. We're an educational 501c3. Our goal is to foster amateur radio participation in space research and communications. That's the official line. The unofficial line is we build and operate amateur radio satellites. We were formed to continue what Project Oscar right here on the West Coast did. They launched the first amateur radio satellite in 1961, and if I remember correctly, it was also the first non-governmental satellite. So we have a long history with amateur radio and satellites. So our early satellites weren't CubeSats, obviously. They were pretty big. The one up top there with the gentleman with the plaid jacket on, that's A07. A07 is kind of special to me. It's 1 month younger than I am. It was launched in 1974. The amazing part is it is still operational. The batteries failed in the early 80s, failed short. Sometime around 2000, one of them opened up, we're guessing. And now whenever it's in illumination, which is pretty much all the time, the transponders operate on it. There's no IHU in it. It's all hardwired logic. Everything has survived for the most part. So that's a 51-year-old satellite that we can go out in the parking lot and talk through if you have the inclination. On the bottom left there, the ring, those were 6 packet store and forward satellites that we launched in the late 80s, early 90s. Those were microsat size, 10 kilogram to about 40 kilogram. And that was some of the first non-governmental store and forward work. The satellite in the middle there, that's one of the ones that wasn't so small. That's Oscar 40. That launched in the early 2000s. That's about a 600 kilogram satellite. That's the biggest thing we've built and launched so far. And then over on the right is AO51, also known as AMSAT Echo. That was a 10 kilogram microsatellite that was launched a little bit after AO40. And a lot of people made contacts through that, talked to each other with just simple handheld antennas and simple FM radios. We shifted after AO51 to building CubeSats for the most part. We've built and operated 5 CubeSats since AO85, a satellite there in the top corner. AO85 was launched in 2015. Additionally, we've provided RF hardware and support, ground station support, for additional CubeSats, most recently HuskySat and MainSat-1. Some of our earlier satellites carried some cameras. It's a little fuzzy, but that picture down in the bottom corner is one of the first images we took back in 2018, North Florida, and you can see the Swanee River winding up there along the side of the photograph. We'll talk about some of the projects we're working on now and what's going on with the organization. AMSAT Golf T is our current project, main project. Hopefully this year, early beginning of next year, we'll wrap that up and have it ready. For us, it's a pretty advanced 3U satellite. We've got deployable solar panels on it. We're flying 3-axis attitude control for the first time in a CubeSat of ours. It has you have to forgive me for some of the terminology here. This was originally written for a completely amateur radio audience. It has a transponder on it, 30 kilohertz wide transponder where you transmit up to the satellite on VHF, and it repeats everything it hears in that 30 kilohertz down on UHF. And that's where we amateurs talk to each other through that. We can also use that for some digital communications, narrowband digital stuff. One of the main purposes of Golf T was to test out a 10 gigahertz high-speed downlink. And that's what we proposed to NASA for our original CSLI. That was the justification for the satellite. And we're also testing a radiation-tolerant IHU on it. Probably everybody in here is familiar with what's going on with CSLI, but we'll see if we end up going with them, if the program comes back, or if we end up on a commercial launch. Another project that we have going is Fox Plus. This is a follow-on to the previous 1U CubeSats that we built. We kind of took a more off-the-shelf approach with this. We built just about everything in the original Fox satellites. In the name of saving some time, we went with some ISIS-space hardware and then our radios. So the antennas and the EPS and everything's ISIS-space, and then the radio payload is ours. We're working on 2 of these. Hopefully the first one will be done this year. It'll fly either a linear transponder or possibly a PACSAT module, and these will be launched on commercial launches. I'll talk more about the LTM and the PACSAT here in a second. The LTM-1, this is one of the payloads that's going to be in Golf T, but we also build this and provide it to universities. Let me explain a little bit about what it is. It's the 30 kilohertz linear transponder. It has a 1200 baud BPSK telemetry downlink, and it also has a built-in command receiver. So we've flown this on HuskySat, Fox 1E, which when it got into orbit's AO109, and then MainSat-1, also known as MO122. We're stepping up production of this to have more of these available. The idea here is that we provide a university that's building a CubeSat with this radio. They integrate it, fly it, use it for their communications with their satellite, and the quid pro quo part is that they leave it on and we get to talk through it when they're not using it. It's worked out pretty well. It's for a program that's looking to fly a satellite that doesn't have a whole lot of funding, this is a good way to go. One of the big benefits that comes with this is that we have software called Fox Telem that we've used with our previous satellites. And with an SDR dongle or an amateur receiver, you can collect the telemetry from the satellite anywhere in the world, and it's sent in to our central server so then the user can have access to it. That's a lot cheaper than paying somebody for a ground station on the other side of the planet. And it's also a little more in the spirit of amateur radio. So we're expanding production on these and hope to have more of those available this year to provide to interested programs. In the same vein, this is what we are calling PACSAT. The PACSATs were some of those satellites that were on the previous picture on that big ring. But these are store and forward systems. They're multi-user. We've got 4 receivers and 1 downlink, and it uses the PACSAT broadcast protocol. So the downlink sends whatever files you're requesting continuously. And as you miss a file, the program, or miss a piece of the file, the program will request that on one of the 4 uplinks. It's a very efficient method. You don't have to spend so much time in retries and downloading stuff you've already downloaded just because you missed a piece of it. So this is a payload. It's just one board, one CubeSat size board. It's designed to be hosted somewhere. It's not designed to be the radio for the entire satellite, but possibly in the future. Again, we're looking to provide these to universities in return for they being run as open access. And again, that's a quid pro quo type thing. You run it as open access, and amateurs all over the world can download your photos or your telemetry files or your data files, experiment data, and send that in. It's a very, very efficient method to get data down from a low bandwidth downlink. We're also working on some more advanced stuff. The SDR Gen 2 is a SDR-based transponder system, multi-band. We can use some up converters to do, we'd like to eventually move to 5 and 10 gigahertz, which are some of our microwave amateur bands, for some higher orbit opportunities. This will be capable of doing that. It's quite a complicated little board, but it has real promise to do a whole lot of stuff in a small package. And you know, we're looking at possibly flying this on a Fox Plus or a Golf mission in the future, or maybe hosted somewhere if we can find a good partner for that. This is a little more directed to the amateur radio audience in general than the CubeSat audience, but we're also participating with ESA has a project called Future Geo. Europe and Africa and part of South America and part of Asia are the beneficiaries of a amateur radio transponder on a geostationary satellite hosted by the Qataris. That is very much something we would like to do here. We just haven't quite figured out the financial aspects of it. But ESA is working on a follow-up program to possibly place another geostationary amateur radio payload, probably mid-Atlantic, because Canada is an associate member of the ESA and they'd like to serve those too. We've had a couple of meetings and initial proposals. AMSAT DL, AMSAT Deutschland is running that. Not funded, I don't think, yet, and we're looking at microwave bands for that. Probably starting at 5 gig and going up to 24 and 47 gig. I'm going to speed through some of these because I got the 5-minute warning. We have an educational program. We are an educational 501c3. One of our big products is the CubeSat simulator. This is basically a non-flight worthy CubeSat on the ground. It does all sorts of telemetry modes. Has telemetry from the solar panels. It'll do a FM repeater mode. It is a great educational tool. And if you have a CubeSat program, you ought to have one of these in your lab to play around with. CubeSatSim.org is the website for it. You can order them. We do them in batches at the AMSAT store at amsat.org. On CubeSatSim.org, there's a 100-and-something page educator's guide to using satellites in the CubeSat Sim in the classroom. AMSAT is refocusing on helping youth get into satellites and learn about satellites. STEM is very important, and we've rededicated ourselves to that. BuzzSat.com is part of our youth initiative, and on there you'll find free online courses regarding different aspects of satellites. I think the first one we did was satellite meteorology, and we've got 5 or 6 of them up there now. Also, you've got a satellite theme coloring book for elementary school kids there. Pretty cool. And we're looking, it's available now, but we're looking to update some of that real soon. So that's an ongoing project. Students on the air. Any ham operators in here, guys, with people with licenses? Got a few of you. So you guys have heard of POTA. Guys and gals have heard of POTA, Parks on the Air. Well, we're doing Students on the Air. It's an opportunity for young people to communicate through the amateur radio fleet. We do it every first and third Tuesday. We have an AMSAT Discord server you can set up to organize contacts. That young man right there is my son, Karsten, KQ4SJM. He's heading this up for me, and you'll hear him on every first and third Tuesday. And we'd like to invite anybody, anywhere to operate it, but especially students, university club stations, individuals. Good place to get together and use what we've got up there. AMSAT runs on donations and membership. We're a completely volunteer organization. No one gets paid a nickel. We need your support to keep amateur radio in space. Please join and donate time, services, information, whatever you got, we're interested. And students, starting this year, students under 25 are free. And this isn't some platitude associate membership. You're a full voting member. So if you're interested in amateur radio in space, come by and join us, launch.amsat.org. That's it. Any questions before we go eat? Wow. And yes, sir. I don't know what the plan is at this point. It's not really our project. We've been participating in it. The idea is to put some placeholders at least in these upper bands. 47 gig is, we don't have anything in orbit, have never had anything in orbit on 47. So I know they were talking about at least a beacon, maybe broadcasting a live Earth image on it, but it's to be determined. Mm-hmm. Yes, sir. We're friendly with them. There's a lot of crossover between our organizations. A lot of people belong to both of them, but they are a separate organization. If you go to the Hamvention next month, we're right next to each other. So, if there were a project that was proposed, I would certainly not be opposed to it. They do a great work. I mean, they're awesome. SatNogs is a open source worldwide collaboration with receiver stations all over the place, and they do a lot of work on initial deployment, taking beacon signals and turning them into accurate Keplerian elements. So they do some important work. Any other questions? Okay, one last thing. About 12:55 or so during lunch, I'm going to set up out front there and listen to the space station, maybe make a contact through the amateur radio repeater on the space station. 12:55 is past time. Thanks a lot.
All right, thank you. That wraps up the session. We'll be back in, so as was mentioned, now is time for lunch. We'll be starting up again at 1:30. So we'll see you back then.
Hello everyone, welcome back from lunch and welcome to session 5 on deployment, simulation, and strategic scaling. Our first presentation is going to be on the Streamlined Assembled Learning Experiment by Kayla Wong and Adrian Cerniak from the Cal Poly CubeSat lab. Please give them a warm welcome.
Hi everyone, my name is Kayla Wong.
Hey guys, I'm Adrian Cerniak. Kayla and I are both third-year undergrads here doing aerospace engineering. We're also the current Sally leads of our most recent flight mission here at the Cal Poly CubeSat lab.
So just as an overview for SALI, SALI stands for Streamlined Assembly Learning Experiment, and essentially the primary objective of SALI was to bring back momentum and experience for students here in lab, because after COVID, there was a little bit of a knowledge transfer gap between students who were graduating from lab and students who were incoming to lab. And so with that goal in mind, SALI was conceptualized, and since then, SALI has been independently designed, manufactured, and tested in-house using resources in lab and on Cal Poly's campus. And all of this was intended to be at a relatively low cost for a CubeSat mission in industry, and also on an accelerated 2 to 3 year timeline for a student-run lab. And with that, our lab hasn't launched in about 5 years now, and so this established to help us get back a project management basis for future CPCL missions. That will be, and the lessons that we get from this will be carrying on into our future missions. And so SALI has 2 payloads, one of them being the CARP microchip, which is essentially a microchip that is studying the radiation faults in orbit, and we also have an OWL radio board, which is a low-power receive-only radio board testing low-power transmission in low Earth orbit. And both of these are from independent Cal Poly research groups, and the OWL radio board is in collaboration with OWL Integrations. And for our stakeholders, our launch broker is Maverick Space Systems here in SLO, and our other sponsor is Cal Poly Noyce School of Computing.
Yeah, just to walk you guys through a bit of our timeline. This is specifically for the flight unit stage of our mission. It took us about 10 months from assembly to then on-orbit operations. You'll see that for July and August, we had a period of about 8 weeks where we had students working full-time in lab on this flight mission. And that's where we did all of the assembly and environmental testing of the SALI flight unit. From then on, most of the work that was being done was just standard flight readiness, licensing, and then getting our ground stations up and running and functional, and then waiting for our launch date, which was, I believe, March 30th, and then a few days after, or a few hours after, we started receiving communication.
And so this mission was driven by a few requirements. So for our in-lab mission level requirements, that just obviously defined our expected behavior while in orbit, and it also defined how our interfaces with our CARP and OWL payloads should be satisfactory. And our launch provider requirements were through SpaceX with their rideshare payload user guide for being on Transporter 16 and being one of their rideshare payloads. And these requirements were mainly communicating through our launch broker, Maverick Space Systems. And of course, we're also on Maverick's NLAS deployer, which had its own requirements, and it's essentially a 6U CubeSat deployer, which is able to hold 2 3U CubeSats that's attached to Transporter 16's payload fairing and deployed us into our orbit. And as for licensing, being a mission and satellite that communicates through amateur radio at ultra-high frequency UHF, we need to obtain a license from the FCC to be able to transmit. And so with that, that trickled down into a few other licenses as well, like amateur radio coordination, and also things like an orbital debris analysis, making sure it would be able to deorbit in the FCC's allotted 5-year time. And as well, we'd also have our NOAA license, which comes from the National Oceanic and Atmospheric Administration. And this license was intended for our payload, which was going to be a low-resolution camera intended to capture pictures of the Earth. But unfortunately, due to some errors in our timeline and going through the approval process with NOAA, we were unable to obtain the license, forcing us to have to disable our camera.
Yeah, and here's just a couple photos detailing our facilities and general operations. On the left there, you can see we do have our own clean room where we did all of the flight unit assembly and functionality testing with the software. Next to that, you can see the final stage of the SALI assembly, which was just the standard side panel fold. And then we also did, on the right there, that's a picture of our long-distance end-to-end comms test, testing not only the functionality of our satellites communications, but our ground stations as well. That was used not with the SALI flight unit, but with our test unit, where we actually took it up on top of Bishop's Peak here in San Luis Obispo and did some comms testing. Additionally, we do all of our environmental testing in-house. So you'll see we do have our own thermal vac facilities. There's a couple here on campus actually, but this one is specific to us and is owned by lab. Next to that is the mechanical engineering department. They have a vibrations lab, and so we use their vibration shaker table for all of our vibes testing. And there you can see on the right is the final stages of SALI in-house here as we prepped it to then hand off at Maverick Space Systems.
And so the final stages of us seeing our satellite was integration with Maverick Space Systems. We went over to their facilities and into their clean room to integrate to their NLS deployer, and that was about mid-February. And then on March 30th is when we launched, and that middle photo just shows the Maverick NLS deployer with that little mark on the red on the bottom right corner in their payload fairing. And then the image on the right is Transport 16's path off of Vandenberg Space Station, and it was a pretty good experience. A lot of us in lab drove down at 3 or 4 a.m. to see the launch, and it was a little bit cloudy, but it was a really great experience for all of us to share.
Yeah, so just to highlight, I guess, some of our key takeaways from this mission that we'll be applying to then future flight missions, and hopefully may provide guidance to anybody in the audience that's looking to do something similar. I guess the main thing we're taking out of this is a better understanding of satellite licensing and the need to start those processes early on throughout your mission timeline, as we left it till the end and it proved to be quite an obstacle, especially when having things such as a camera on board. So yeah, that taught us how to make, I guess, trade-offs with mission requirements and our stakeholders, and inevitably led us to disabling the camera, as it was, I guess, more of a priority to launch our payloads and sacrifice being able to take photographs. Additionally with that, it was a great experience learning how to communicate with other lab members, coordinate teams of people together in subsystems, especially in an undergrad environment. It's definitely hard to coordinate people's schedules when everybody's full-time students on top of participating in our lab projects. So it was a good experience on how to be adaptable with schedules and make priorities.
And so for our current and next steps that are happening right now, we're still doing on manual operations as of right now. And as of yesterday, actually, we were able to successfully power on the OWL payload, and we're able to receive its status. And so once we're able to also turn on the CART payload, we'll complete a power budget analysis, because as of the first 2 weeks, we have been power positive, generating enough power with our solar panels instead of draining the battery voltage. And so along with that, along with the power budget analysis, we'll also have to establish which TLE is ours. As of right now, we are using SpaceTrack's TLEs. At first, initially, we propagated our own TLEs and wrote scripts to propagate and determine where our initial contact would be. And since then, we've tracked down our TLEs from SpaceTrack to about 3, and recently we are pretty confident in 1 TLE, but SpaceTrack's orbit determination still isn't optimal right now because of the small size of Sally. But once we are able to establish that TLE, we assume all of these processes will take us about 1 to 2 more weeks. But once we nail that down, then we'll be able to automate our operations. And so the expected mission lifetime of Sally is estimated to be 2 years, and we're also expected to deorbit in an estimated 3 years. And so with that 2 years of a functional satellite, it will not only bring us operations training for members in lab, but it'll also just allow us to carry on the lessons and the experience and the data that we collect, and also like the procedures and the tests that we ran, and carry these lessons and experiences on into future missions for current lab members for our mission, like the AMSAT mission, and also just incoming lab members in the future.
So yeah, just a quick thank you, I guess, to Maverick Space Systems for providing us a launch opportunity, as well as the Noyce School of Applied Computing here at Cal Poly for funding the whole project. To anybody in the audience, I know there's a lot of undergrad projects here. I know there's other universities present right now. I hope this, I guess, just gives you guys maybe a little guidance or a little input on how we do our operations here, and hopefully that can help and support you. Feel free to reach out to either of us at our emails, or you can ask questions now if you want any guidance or help. I know there's a couple people from Davis here. We're going to be doing vibes testing with them later on in the week. So, I mean, we are interested in helping out other groups and other labs, especially if you need help with facilities. As I stated, we do a lot of stuff in-house here.
Yes.
How do your simulations for power, command control perform versus actual data?
Well, we are still kind of in the process of analyzing all of our data right now, but the main thing that we were able to take away is that without powering on our payloads, we were still power positive, which is a great sign to see. But we do know that our payloads are the main, draw the most power out of anything on our satellite, so we'll have to just complete that power budget once we turn both of the payloads on.
Any more questions? Cool. Thank you, guys.
Thank you.
Our next presentation will be by Francesco Esposito from D-Orbit on In Orbit Now, Services for Satellite Precise Deployment and Technology, IOD.
Hello. Hello, everyone. Good afternoon. I'm Francesco, and I'm here today representing D-Orbit. D-Orbit is an Italian company that wants to create the first space logistic infrastructure. This means that we want to enable circular economy space. So this means we want to ensure that all the resources are used in the most efficient way, reducing at minimum all the wastes. For the moment, we are at the first step of this path, so we are focusing on the optimization of satellite business and performances. And just to give you some numbers, we are pioneer in space logistics. The company has been founded in 2011. We are now more than 600 people. We are growing year by year. We carried out 24 missions, launched 22 Ion satellites. That's our satellite. I'll focus on it later. And we brought to space more than 210 payloads. Our headquarters is in Italy. We also have some other offices in Italy, as in Europe, such as UK, Portugal, Greece. And we also have one in US, in Boulder, Colorado. We work pretty much with any kind of customer, mainly from new space market, but also from traditional space and institutionals. And of course, they are from all around the world. But what do we do? We have different services. As first, we have standard launch services and space transportation services that are the main focus of today's discussion. But we also spend a couple of words on space cloud services and satellite as a service. And finally, we are also developing the in-orbit service. So we signed a contract with the European Space Agency for designing, building, and launching, in a couple of years from now, a satellite that will go to geostationary orbit and will dock with another satellite to perform some activities such as close inspection, attitude change, and orbit change. But as I said, let's focus on the first two, so the orbital access services. These are the services that we provide to our customers to bring them to orbit, as you can understand by the name. So, first of all, standard launch services. This is for CubeSats and microsats. So let's consider one of the typical mission, rideshare mission from SpaceX. If you have a CubeSat or a microsat and you don't have any particular requirement on the release orbit or on the timing of the deployment, we can just integrate your payload on board the launcher and let it be deployed by the launcher on the release orbit. This service includes capacity procurement from the launcher, separation system procurement, so dispenser for CubeSats and separation ring for microsats. We act as interface between the customer and the launch vehicle provider. So, for example, we provide support in the document exchange. Of course, we provide the integration service. We have a lot of experience with CubeSats and microsats too, with a lot of external suppliers of separation systems, but we're also developing our own separation systems that will be ready in very few time. So, I said, let's assume that you're fine with the rideshare deployment orbit. But what happens if you're not fine with it? That's why we came up with the space transportation services. So here on the right, you can see our platform. That's Ion. Ion is an OTV, so an orbital transfer vehicle. So it is a microsat that is capable of maneuvering. And basically, we can solve the orbit issue because we can integrate your payload, your CubeSat or your microsat, on board our platform, and we can just maneuver and eject your payload in the desired orbit. Ion is able to carry up to 64 units of CubeSat in total, and up to 200 kilograms of payload mass. This is an overview of Ion performances. One thing that is important is that, as I said before, we already launched 22 of Ion. So this is something that we did, and we have at least one Ion on board each rideshare mission. So this provides our customers a lot of flexibility. This is a video of the deployment of Ion from one of the past rideshare missions. And I said before that we're able to maneuver. So let's see which kind of maneuver we can perform. First of all, the altitude change. We know that we have no power in choosing the orbit of the rideshare missions. So if you're not fine with the altitude chosen by SpaceX, we can just adjust the altitude and release you in the orbit that you want. So practical example, you can be the altitude of release, the release altitude of SpaceX, maybe it's too low for your target in life orbit. So we can just increase the altitude in the release, but we can also decrease whatever is your requirement. Then, true anomaly phasing. This is mainly for customers that have constellations. So we know that constellations are designed to work in a precise relative geometry. And to get that geometry from a standard rideshare mission, you have two possibilities. You can put a thruster on board your CubeSat, but this would increase the mass, would increase the cost. Or you can achieve that through differential drag maneuver. But you know that this takes a lot of time, and time is precious. So we can reduce that time up to the 85%, get your constellation in the exact geometry that you want, and enable you to produce revenues faster. Plus, we can also perform the run shift. So if the local time of the ascending node of the rideshare mission is not fine for you, we can just adjust and target the right plane. But that's not all, because with our platform, we can also provide the hosted payload services. So let's assume that you have a technology or an experiment that you want to test in space for maybe a few times. So maybe it's not worth to build a CubeSat just for a few times. In that case, you can provide us with your technology. We can integrate the technology on board our platform. There are some standard interfaces. And that's it. We take care of all the rest. So basically, you provide us with your experiment. We integrate it on board our platform. And then we provide power. We provide attitude capabilities. We provide downlink and uplink. We provide, we operate your payload. So literally, you can just give us your payload. You tell us what you want to do. And we will give you the results of your experiment at the end of the test. On the right here, you can see a picture of a mock-up that we use for conferences. This picture is interesting because we can see how the payload base is highly flexible. So it is possible to put on the same mission both CubeSats and hosted payloads. And here we can see a very cool video because it is a perfect mix of the two services that I just described, so hosted payload and CubeSats. Here we can see CubeSat released from our platform. I don't know if the video is going to start. No. Let's see. OK, no video. So it will be for the next time. Basically, it was a deployment of a CubeSat from a camera that we had on board as hosted payload. So we test we use the camera for showing the deployment of the CubeSat. Then, satellite as a service. If you have a technology that you don't want to demonstrate, but you have a complete technology, and you want to put different nodes into orbit, we can provide you our satellite. So with no need to build your own platform, you can just rely on our platform, on the fact that we have heritage, on the fact that we have a lot of ions on all the next rideshare missions, as I said. And you can put your technology on board our satellite and exploit and make a constellation with, let's say, just focusing on your technology. Finally, we have space cloud services. So what if your technology is not an hardware, but it is a software? Maybe also in that case, there's no need to build a CubeSat. You can just upload your software on board an existing platform in space. So you can provide us with the software that you want to test. We can upload the software on board our satellites. We have intelligent nodes with sensors such as cameras or any kind of sensor. And we can feed your algorithms with those sensors and test them in a proper environment. Of course, this is good for both IoT, but also if you want to have different sources of data in space, so you can upload your software on different satellites, gather information from all those satellites, and elaborate them and just download the information that you require. So this is pretty much what I had to say today, guys. Thank you for your attention. Should you have any questions, I'd be happy to answer. Thank you. Yes, please.
What is the legal framework that you use for your launches? For example, customers' CubeSat, what sort of licensing would it require for you to launch?
Thank you for the question. The question was, which kind of licensing is required for CubeSats that we integrate on board our satellite? Licenses are, we don't require any license. We just require the customers to apply for their licenses for communications and so on. So from our side, there is no license that's required. Yeah. Okay. Thank you, guys.
Our next speaker of the afternoon will be Keith Cleveland with Cleveland Aerospace Technology Services, discussing CATSIM, a cloud-based CubeSat mission simulator for early phase design, digital engineering, and education.
Good afternoon. So I'm Keith Cleveland. I'll be talking about a CubeSat simulator. If you haven't figured out, Cleveland Aerospace Technology Services is acronym CATS. So that's why it's called CATSIM, because it's fun. All right, just a quick little blurb about me. So I've been in the aerospace industry for 20 years, worked on some missions for NASA here and there. Cleveland Aerospace provides program management, system engineering, and technical assistance, space acquisition, advisory services, mission assurance, and digital engineering support. And then today we're going to be talking about the CATSIM CubeSat simulator. So one of the challenges that I have discovered in industry, it's not just related to CubeSats, but there's a lot of fragmented tooling that exists in the engineering space today. There's a lot of reduced traceability moving throughout, a lot of barriers to entry for maybe some startups, some university teams getting started, and there's always an increase of risk of errors that happen throughout the early phase design process. What I think that the community needs is increasingly mission ambition. So CubeSats are not just an idea of trying to do things related to space. They're progressing towards scientific and technical endeavors. Their development velocity is increasing in speed, and there's always evolving requirements that are going on now throughout just the world, frankly. There needs to be an enhanced tool to bridge some of the communication gaps between diverse engineering, scientific and management disciplines. There's an accessibility issue where some of these tools are incredibly expensive and they need a lot of computing power and a lot of inherent knowledge that goes into them. And there's just a need for early integrated phase in simulation. All right, so introducing what CATSIM is. So it's a browser accessible platform. So it works on cell phones, Chromebooks, tablets, pretty much any platform that has a web browser on it. It does do integrated mission analysis. So that's orbital modeling, ground track analysis, subsystems estimation, and mission insight. It's a very versatile application through both in-depth technical mission studies and effective instructional use. All right, so talking about some of its capabilities here, so orbit propagation. So it does reasonably accurately model and predict the trajectory of spacecraft over time, so it includes drift. It does provide some 3D visualization tools for you. It does have eclipse awareness embedded into it, so if you go on the other side of the Earth, it acknowledges that. It does provide some sort of power estimation and forecast for power generation. There is a rudimentary thermal analysis included in that. There's mission geometry, and there's early design trade support. Okay, so some of the mission concept, the first order insight. So you can define the mission parameters. So you establish a core objective, scope, and key performance indicators. Visualize the results. And then you simulate the orbital scenario. So like I said, it kind of ties together with the visualization that this has. And then you support early design choices, environment life, and subsystem effects, and inform requirements discussions. So this is a tool to get through the early mission concepts into something that's actionable as quick as possible. Just a little bit more on the orbit. So there is a 3D orbital motion, and then there's key orbit metrics that are involved and aligned ground tracks. So this simulation will actually provide you a ground track so that you can look at what communication nodes you need on the ground, at least give you a first order idea of what you're dealing with. And this unified, it's all visual context, empowers users to rapidly grasp mission geometry and its implications, enhancing decision-making and operational understanding. So this really provides a gateway to do thought processes very quickly. It is not meant to solve all of your mission design issues, but it's there to get you there as fast as possible through the early phase discussions and trade spaces and engineering design. So it does have a power and thermal assessment in the simulator. So it does estimate power consumption. It does take into consideration, is it on synchronous orbit? Is it all the different orbits that we associate with satellites? It does model the battery state of charge during the orbit and during the duration of the mission. It does access the thermal behavior across the spacecraft attitudes and mission duration. It does look at the early life cycle feasibility screening, so it will give you an indication if your input into the tool is a good idea or bad idea very early. So it provides very rapid assessment, and you can change it. So if you change the input from one thing and it looks like it's not going to work, you can literally sit there and 1 minute later change the input again and see what happens. So it's a very quick responding tool that you can use to evaluate things. One of the things, there's some feedback that I got was when you go and submit a proposal, there's always an ODAR requirement associated with that. And so this tool will talk about the compliance to the ODAR requirements that NASA has and the government has as a general statement. So it'll project the duration of the object in orbit after its operational life, so it'll tell you how long it'll take the orbit to decay. It does look at the compliance status, right? So it will pull whatever the latest NASA requirement is and pull that out of the NASA requirements in their database. And it shows whether or not your mission will meet it or not. And then it actually generates a narrative for you that if you wanted to, you could put in your proposal as a compliance for that. So it's a good facilitator on knowing whether or not your mission is going to meet the ODAR requirements or not. All right, so a little bit about what speed, accessibility, and what a shared understanding would look like. So like I said before, it's very rapid. What used to take, like in a traditional mission, even if it wasn't a CubeSat, maybe it was something a little bigger, it could take months, if not a year or so, to go through things. Now you can do it in what would take that amount of time in maybe a day and a half. It does validate it very quickly. It's almost real time. It provides very quick turnaround time for trade studies about what you can do or not, the requirement discussion, subsystem awareness. It does provide you some documentation, and it does allow you to talk with your stakeholders very quickly. Whether your stakeholder is a professor that's trying to be a PI for a mission, or if it's a scientist actually located at like NASA Goddard or something, if you want to talk very quickly about what those first order requirements are, what it does to the mission, this allows you to do that in almost real time. So what was this built for? So it had education in mind. It also had as a workforce development in mind. So it kind of demystifies a little bit of the complex nature of trying to come up with a concept for a mission. It does allow for the student-led teams to go through those exercises of developing their missions a lot faster at a much higher feedback rate. It does provide some training environment for some of the younger early career engineers. It's very interactive. It does have advanced visualization. Just a caveat there, advanced is used in the fullness of what that word means from a visualization point of view. It does have a first order engineering insight. So that's why the development of this was kept in mind. And so you can use it as a design course, use it for flight projects, early feasibility studies, proposal support, concept of operations discussions, internal trade studies. The whole idea is that it's a tool that allows your idea to come to fruition as quick as possible so you can get past that first order design step. So what makes it different is that it's accessible. Like I said, cell phones, iPads, Android tablets, Chromebooks. Basically, if it connects to the internet, you can use it. It does look best on a computer, just as a caveat there, but it does work across all platforms. This is cloud-based. It is very specifically mission-focused. There's nothing else in there, and it is a high-fidelity tool. So I used existing missions and their data to backstop it, and that is open in the simulator. When you go through the tabs, you can actually set it to one of those missions, and it correlates directly with how that mission operated in space. And so a little bit here about where this is going. So I do want to get to the second order subsystem models. That is obviously a lot more complicated, a lot more goes into that. I want to go into the advanced scenario analysis, so developing a more sophisticated method for exploring complex operational environments and mission outcomes. So when you talk about first order, second order, and so on, you can also annotate it to like a concept study, preliminary design review, a critical design review. The end goal for this is so you can go from idea to building hardware as fast as possible. Stronger digital engineering integration. So the connection between, deepening the connection between the connection and synchronization with digital engineering tools and workflows. So this is supposed to complement other tools that are currently in use in industry, use in the government, use in academia. It's not supposed to replace them. It's not supposed to compete with them. It's supposed to complement them. And so getting some user feedback and trying to roll that back. So collaborate workflows. So now in this digital age, we use Microsoft Teams and all the Microsoft products where you can basically do a live edit with 17 different people across the world. So I also want to get to a point in time where we could do that since this is cloud-based. And then the big thing that I want to do is that instead of having an engineer or a student or somebody input the parameters for the mission concept, I want you to put in a science objective, right? I want you to say, what do I want to do? Do I want to go spend the Aurora Borealis in the Northern Hemisphere? Do I want to look at the solar radiation effect on the magnetic cusp. Like you put that in, and then you have an AI decision engine that goes through what would be similar to a Monte Carlo analysis, and that spits out a mission for you. And so that is where we're going, probably in the short term, is putting a decision engine associated with this model to make it even more of a early decision feedback loop, to open up the space to even non-engineering folks and non-technical people. All right, so some of the key takeaways here: digital engineering, so it facilitates a model-based systems engineering approach for integrated mission simulation. Education, provides some hands-on learning, hands-on tools, and then it very much does early phase mission design. And so it unifies the concept work into integrated visual and practical CubeSat mission simulations. So there's a QR code there, so that'll take you straight to the simulator. It will work on your phone. It does require a login, so you can use your Google login if you want. I have, for a limited time, I have made it free. There will be a cost associated with it in the future, but I want people to try it. I want to get some feedback. I want to know what works and how it doesn't work. So you can scan that. It's free. You can also go to clevelandaerospace.com. There's a tab that says simulator link. You can use that as well if you want to do it on a computer later. And then there's information to contact me with any questions. Speaking of questions, do we have any questions? I stunned everyone with my amazement. Ooh, there's a question all the way up there. Wow. So the question was asked about, we'll just say GNC control. Is that okay? Is that okay? So one of the things that this does, it does not include a comprehensive GNC control subsystem yet. It assumes that it's basically a free flyer, that you put it in orbit and it stays there. It does not take into account for the attitude monitoring that you would have on a mission. So I'm not there yet. I'm working on it. Yeah, so that's actually, so you asked about the only subsystem that's not included yet fully in the simulator. So thank you for that. Appreciate that. Sir. So the question was, I'm going to rephrase it slightly, so tell me if I got it right. So how does this early mission modeling fit into later mission modeling / maybe execution? Maybe that's a good word to use. So this is not designed to replace STK. It's not designed to compete with it. It's not designed to replace GMAT or any of those systems. It's designed to complement it, right? So this is very early mission phase things, because so a little bit of context, I'll go a little off script here, is that so the government has, phase A, phase B, step 1, step 2 proposals. And so this is to streamline that process to get you to where you can get to that second order of decision making and designing when you get to the PDR phase as fast as possible. Oh, so yeah, so you can export to a JSON file, and you can export some of the data through like Excel and a few other things. So you can take the data out of this simulator and put it in a form where you could put it into another platform. That's why I did that. So you could also take it out and put it into a proposal if you wanted to. So that's why I did that. Please. So it hasn't, okay, so the question was, is orbital perturbations, does it account for it? Does it have a scenario that accounts for it? So The answer is mostly yes, and I'm going to answer it this way. So there is a drag coefficient that you would input into the simulation. So there is some knowledge that you have to have as an individual to put into it, but it is a parameter that you can put in. So like if you had solar radiation resistance or something of that order, you can put it in there. It's captured as a parameter as just drag as a general statement. So I will use the engineering colloquial term of first order. It is an initial assessment. It is not supposed to be the final assessment, right? So it is to get you that final assessment as fast as possible. That's the idea, right? Because there's already existing tools. Actually, there's some really nice gentlemen out there at the table that have existing tools that get you to answer your exact question. So I'm not going to try to duplicate that or compete with it. I want to get you to use those tools as fast as possible. So that's how I try to do it. And we have time for one more. All right, sir.
Does it have a model of the Earth's magnetic field?
So you keep pointing out things I haven't done yet. There is a coefficient in the back end of calculations that makes an assumption that I would not call as 100% accurate. It's a mathematical coefficient that covers a reasonable majority of the magnetic field. So like I said, this simulator is not the end-all be-all. It is to get you to make really good decisions as fast as possible, right? So if you want to play around with an idea, like you're sitting at your desk or whatever, and once you want to get to a point where I can write a proposal about that, that's what this is supposed to do. Yeah, it's not supposed to get you all the way to the end. That's not what it's meant for. All right, I think I will end there before I get yelled at. Thank you very much.
All right. Please welcome our next guest speakers, Kyriakos Philippou and Jonathan Kay, presenting on Genesis, applications of advanced monopropellants in a nanosatellite engine system.
Hello. Hi, my name is Kyriakos.
And my name is Jonathan.
We are the mission leads for Genesis, the Genesis project. We'll be going over today just like a little bit about Genesis, a rough overview of the mission, kind of some of the ideologies behind some of the decisions that have been made. So I'll start us off here with just some quick historical context. A lot of you might know this, but so the CubeSat standard was introduced in 1999, actually in part by someone from here at Cal Poly, as well as Stanford University. They created the first model of a CubeSat, which would go on to become what is now a much larger industry. It enabled low-cost development, so it kind of opened satellite creation to a lot more people than as it was available before. As of now, it's a $520 million industry. I'm sure that number has grown even since 2025. There's a lot of money in CubeSats now. Our laboratory here has launched over 13 projects and supported over 175 different satellites. And so we've done a lot, but the point of the Genesis mission, or I should say the Genesis project, was to investigate something that is not super common, which is propulsion in CubeSat technologies. Approximately, so less than 9% of CubeSats as of 2024 are actually using propulsion systems like thrusters. So the purpose of this, of Genesis, is to investigate that specifically through advanced monopropellants.
So first, I would like to give like a brief overview of what a monopropellant is and how monopropellant thrusters operate. Typically, in a thruster, you have both a fuel and oxidizer that mix to combust, and that's how you get your thrust. But in a monopropellant, your fuel and oxidizer are self-contained within one chemical formula. And this fuel is then fed into a catalytic bed, which contains material that speeds up the rate of decomposition. And that then creates the hot gases that are spit out through the nozzle. And monopropellants are a better solution to thrusters in small sats because you only have one fuel and you don't need to carry as much of a larger profile in your CubeSat.
So immediately there are some barriers to using monopropellants in satellites. The most dominant fuel, monopropellant, is hydrazine. It's very simple, but it's unfortunately extremely toxic. And it requires, there's a lot of costs. You need scape suits to use it. You need very specialized facilities. There's a lot of concerns with storing hydrazine, especially long term. It's really easy for it to degrade, and then you get issues with like pressure vessels. There's just a lot of concerns with actually dealing with hydrazine, and the primary one is its toxicity, I guess as well as its cost, which just makes it not available, especially for our program. We're a student-led program, and the idea of having these several $100,000 suits and facilities and everything is just not available to us. So that's kind of one of the big issues initially with using monopropellant technology, at least for us, for small sats.
And so this is kind of where advanced monopropellants, also formerly known as green monopropellants, come in. These are non-toxic alternatives to hydrazine. An example is AMSAT, the fuel that we'll be using, that was developed by the US Air Force Laboratory. But the main benefits of using advanced monopropellants are they have much lower toxicity, which reduce the safety infrastructure needed to handle and use the fuel. And they have comparable and even in some cases, improved efficiency, with AMSAT being one of those cases where not only is it safer to use than hydrazine, but it is much more efficient with a higher ISP of 266 seconds at 300 PSI. And so this is, I guess, the solution for smaller scale uses for us as like a university to be able to use monopropellants.
With that being said, there's still a lot that goes into it. So I have it kind of broken down at the bottom here, but if you include all the costs, it comes out to about $8,000 a gallon of actually being able to get like I don't want to say in your hands, but like to have AMSAT within arm's reach. There's a lot that you still need. You can see here though, so this is a chemist who is actually involved in the creation of AMSAT. And that is AMSAT in his beaker there, and he's holding it, and he doesn't have any face mask on, no scape suit, anything like that. So it's significantly better to be around than hydrazine, which makes it much more available for us. There are some, and these are concerns that we have had meetings about and that we've discussed, and will end up and have been big roadblocks in the development of the project. Is things like getting high enough rated storage to be able to store AMSAT in the quantities we'll need it, and transportation costs. There's a lot of very specific niche things about transporting AMSAT and similar fuels that has made that kind of a roadblock. So there are still some challenges regarding cost and the equipment necessary.
But we're still going to continue talking about what our project is going to look like. Our initial stages consisted of trade studies and initial design research. And we've moved on since then and are now working on thruster sizing and design, along with component selection as well. For our project as a whole, our main deliverable is designing a thruster that can be used potentially in a CubeSat. And our main deliverable is firing it in TVAC and characterizing its performance, both getting a thrust value and ISP. But from For starting now, we are looking into thruster design and component selection, and then we'll move on to manufacturing, which can be done either here at the Cal Poly CubeSat or Cal Poly's machine shops, or can be outsourced to other shops. And then we'll move on to thruster assembly, which will happen in our clean room, and then testing, which will happen in the Stella TVAC chamber, which is here at Cal Poly itself.
So we mentioned it earlier, but our fuel of choice is Ascent. And Jonathan had mentioned a few things about why we had specifically chosen Ascent. There's a few green monopropellants out there, or advanced monopropellants is the official term. So this is Ascent. It was previously, it had an like a AFRL description, AFM315E. It's been given a little bit of a nicer name now. But there are a lot of it, so even not counting the safety, improved safety you get by using an advanced monopropellant, there's a lot of advantages to using Ascent. So it has a reduced footprint for the same velocity impulse, and equivalently, you can get increased velocity impulse for the same footprint. Ascent has 50% higher energy density than hydrazine does, which makes it ideal for small sats where every gram matters. And it also has a 10% higher specific impulse than hydrazine, which are both factors that went into its consideration. And then because it's not as dangerous, or at least it's easier to be safe around it, there's a lot less, there are fewer costs that go into actually handling, like teaching personnel how to handle the fuel and the facilities required, and any specialized equipment. We saw on that other slide that it was just being held in a beaker, and that's open to the air, and the extent of the protective equipment was basically gloves. So it has a lot of those kinds of things, which makes it very ideal for our purposes.
Currently, like I said, we're working on catalyst and nozzle design, but additionally, we're also working on test stand development, which is a big part of what we're doing. Our current choice for testing our thruster is using a torsional pendulum that has frictionless flex pivots, which we're currently planning on using a laser displacement sensor to measure this displacement of the pendulum to then characterize thrust. But we're doing the development of the test stand along with the development of the thruster itself. So that way, as we're making progress in the thruster, we can figure out what we want our control systems to look like and how we're actually going to implement it with our thruster. But currently, we do face some challenges in design, especially when it comes to the catalyst bed and degradation. Monoprops usually burn very hot, especially Ascent. It can burn over 2,000. Decomposition temperatures can be over 2,000 degrees. And so thermal management solutions are a large area of interest for us. Additionally, material selections play just as much of an important role in making sure that we can minimize catalyst degradation as much as we can. This is a huge challenge because currently our idea is to use a granular structure for our catalyst, which means we're going to have a bunch of pellets packed into our bed. And though this is great for exposing our fuel to a large amount of surface area, the high temperatures can cause the pellets to degrade, which can then clog the bed, redirecting flow in concentrated areas. And that concentrated flow can then cause hot spots, which will then further contribute to the degradation of the bed. And this as a whole will affect the efficiency and the lifetime of our thruster. And so these are just a few challenges that we're facing and things that we're keeping in mind as we're designing. Like I said before, solutions include material selection and thermal management solutions, which we are also going to be looking into going forward.
Overall, though, there's been a lot that we've learned from Ascent, and from Genesis, I should say, but from Ascent as well. There's been a lot that we've gotten from it. Like Jonathan mentioned, there was a lot of design considerations. There was a lot of student development that happened with understanding the extent of those design considerations, how to handle modeling a thruster for such a small form factor while trying to keep the thrust like an actual number. There's the test stand was an interesting, there was a lot that went into like designing the test stand, choosing how we were going to measure it. And then data acquisition, there was a lot of trade studies that were done. So a lot has been learned from that. And then with propulsion, there's quite a bit that you could do and that we're hoping to eventually be able to do. The long-term goal, and this is very long-term, Genesis is being made to fit within a CubeSat form factor. So the eventual goal is that we will launch a mission that will use Genesis on board. And we'll be able to do hopefully a lot more with this mission than we have been able to with the past, because we'll have actual, like we'll have collision avoidance. We can control our deorbit time incredibly well. And then orbital maneuvers will be more available to us. A lot of our our deorbit time and orbital maneuvers and everything on previous missions have come from passive systems. So having an active system is something very, very interesting to us. And the idea of being able to do a mission that's more complex or advanced with Genesis is really exciting. So we're really looking forward to the future. I mean, it'll probably be a little far away, but hopefully it'll be exciting. Yeah, so thank you so much. Do we have any questions? Oh, yeah.
So have you surveyed the various launch providers and figured out which ones feel that that's safe enough for a CubeSat kind of payload?
Not yet. Like I said, Genesis is still in a lot of the very early stages, so there isn't really much to present to them as of right now. In the future, though, that is definitely something we will consider. It's a great idea. And it should be noted that there have been missions that have flown with Ascent before, so it won't be like this is the first time the fuel has ever been used. But for CubeSat systems, it'll definitely be interesting due to the way CubeSats are stored on board. Yeah, thank you.
And also, just to emphasize that this project right now is just an R&D mission and not an actual flight mission. And so those are not exactly questions that we're looking into currently.
Can we get the next one?
Mm-hmm. Yes.
Did you set on what are the ideal materials for the pressure chamber and nozzle?
Right. We have looked into potential materials. One material in mind is called rhenium, and a rhenium platinum alloy is something that has been looked into. Another compatible material is called TZM as well, which I don't think has been explored as much, but those are just two options that we're considering. But for us, our main concern is, again, like thermal management. And so finding materials that can, I guess, endure the heat from decomposition is a big priority for us. But those are just two that we're considering right now. Mm-hmm.
How small do you think the thruster could be made?
The thruster is going to be pretty small because, like I said, we're aiming for 0.5 newtons of thrust, which that drastically reduces your mass flow rate, and that will impact your sizing for both your nozzle and your chamber, which in this case is your catalytic bed. And so it can easily fit in the CubeSat form factor, but because the thruster is really small, again, like we were talking about, thermal management is going to be a big issue because it's a lot of heat that you're putting in a very small footprint. But yes, I can't give exact sizes or anything like that, but it'll be really small. Mm-hmm.
Yeah, over here.
When you guys were kind of considering which kind of propulsion method to use, did you guys consider electric propulsion? And if you were, what kind of factors did you take into play, which kind of led you to go towards more of a liquid propulsion method?
Want to do that one?
Yeah, sure. So the project was contracted to us as a project that we will use Ascent in. So I guess from the very beginning, we were kind of set on using Ascent rather than using other modes of propulsion. Yes?
Do you have any concerns that the launch vibration environment could cause, displacement or damage to the catalytic bed?
Yeah, that is, I guess, an area of concern that we haven't looked into too much because, like I said, it's not necessarily a flight mission as of now. But going into the future, like if we were to fly it, that would be something that we would look into for sure. From what I've seen though, I think the materials used in the catalytic bed are pretty strong, like materials that have very high thermal capacities, or at least the metals and alloys that we're looking at typically are pretty mechanically strong too. And so, yeah, that would be, I guess, something that we look into the future, but not necessarily a concern as of now. Yes.
For sizing goals, you said you want to
Mm-hmm.
CubeSat form factor. Are you referencing like a 1U, or do you think there'll be something bigger like a 6U to host the system?
As of now, we're really just thinking of fitting the thruster assembly itself inside of 1U, which is definitely doable. If you just looking at your chamber, your nozzle, and your injector, or whatever feed system you have. Going into the future, though, like as you said, we'll have, if we were to implement it into a CubeSat, you'd have to have thermal management systems, and also fitting a tank inside and everything is, you know, that will take up probably more space than a 1U. But again, we're just kind of keeping that in the back of our mind while we're developing this mission. It's not necessarily something that we're focusing on, but yeah, probably around 1 to 2U is what we're thinking about. Any other questions? All right, thank you.
All right. Our final speaker of the session is going to be Steve Dunton with Cal Poly and OWL Integrations, discussing OWL Integrations squad payload.
All right, good afternoon. I'm Steve Dunton. I'm accompanied by a couple of our graduate students in electrical engineering, Sammy Brunton and Kevin Notberg, and they're going to be doing most of the talking for this presentation. So this is officially called OWL Integration Squad Payload. We like to call this Ducks in Space. So we've had a multi-year collaboration with a startup company, OWL, that makes radios, and just to confuse it with all the bird terminology, they call their radios ducks. And we've been on a multi-year journey with them that originated when they became intrigued by some of our students who were doing high-altitude balloon testing. And they wanted to test their radios in a balloon because that's a way to get long range, they thought, easily. And that resulted in them learning about our CubeSat program and becoming fascinated with the idea that they could fly their duck radio in space. And so we've been on a multi-year journey. We've presented here before, initially on their funds and our own funds, evolving their electronics, because we do more than just fly things in balloons or satellites, evolving their firmware, testing in a space environment. Cal Poly has all these wonderful facilities. Hopefully you've seen them on the tour. We have, of course, we have ground stations, but we have clean rooms, we have shaker tables, we have thermal vacuum chambers. We put these on drones. Those wound up getting easier to fly than balloons. And when Sally, which you heard about earlier, came along, we had an opportunity to fly as a hosted payload. And this payload is currently flying in space. So we now have a duck in space. This is the plug for our customer, our sponsor, OWL Integrations. OWL stands for Organization, Whereabouts, and Logistics. They came out of a hackathon environment, and their mission in life is to provide connectivity where it doesn't exist, either because it's in a remote location, think maybe exploration, or because the infrastructure has been destroyed. They came out of Hurricane Maria in Puerto Rico, but you know, the hurricane, the ice storm in California, the fire, all those things can take out your cell phones or your cell towers and wipe out communications. But if you have their radios, a little larger than my clicker device, one radio can connect to the other, can connect to another, can connect to another. They form mesh networks, and that's how they move data around. Their radios support low data rate communication, primarily text. You can connect to them to an app on your phone, but and potentially voice. And so, again, their initial product was this handheld device. What you're going to hear in the rest of the talk is Sammy's going to give you a reminder about the Sally, who is our host spacecraft, and then Kevin Notberg is going to talk about the payload, what's in the payloads, how we developed it, how it compares to some of our other products, as well as how we tested this and verified that it was appropriate for this type of mission. And so I'm going to turn it over to Sammy. And here's your, oh, there you go. Here's the clicker.
All right, so SALI stands for Streamlined Accelerated Learning Experiment, and we launched on March 30th, 2026 on SpaceX Transporter 16 as a rideshare with Maverick Space Systems. And the main focus of this was to develop a low-cost CubeSat. And it was named after Dr. Sally Ride, which was the first American woman in space. And this really showcased Cal Poly CubeSat Labs' end-to-end CubeSat design, build, and testing capabilities. And the 3 independent payloads on SALI were OWL's Squad payload, which we'll be discussing in this presentation. And then there's Cal Poly Computer Architecture Research Project, CARP, who's focusing on radiation effects. And then a camera payload, which had to be disabled due to NOAA licensing issues. And this is going to lay the groundwork for future CPCL missions. And we have successfully been deployed, and we've had early communications. Now from Kevin.
Yeah, so a quick introduction on kind of our research team with OWL here at Poly is kind of focused on 2 things. The first charter is we're focused on creating domestically aligned electronics to replace their hardware. An OWL device needs to have LoRa. That's how they build their mesh networks. It needs to have GPS for tracking assets. It needs to have Wi-Fi to connect to people's phones or Bluetooth. And then it needs compute, power, and a battery management system. And so we started a program called QUAD, which stands for Quackerboard Advanced Development. It's focused on realizing that in various architectures and studying what might be a suitable architecture to replace that electronics. The second main charter that our team has been focused on for the last 5 years is taking OWL's electronics and deploying it in extreme and challenging environments. And we've put it on drones, we put it underwater, we put it in high altitude balloons, and now we're trying to go to space, and we have. So we started the Squad program, which is just Space Quad, and it's taking the electronics we realized on Quad in LoRa, compute, and power, and putting it in a form factor that is suitable to interfacing with the SALI payload. So, to make sure that we are sticking to that research goal, we don't need GPS in space. We don't need battery management system in space because it is provided by SALI, our power to Squad. We don't need our Wi-Fi in space. We only really need power system, DC-DC, compute, and our LoRa transceiver. And so Squad is just a transpose of all those core features onto a new board. And it's close to the exact same system that we have on the terrestrial handheld radio that you saw on the last slide. Only changes where we added some temperature sensors, we added a non-volatile FRAM to the system, and we upgraded the program memory flash to an industrial grade temp flash. Oh, I went back, sorry. So kind of a quick introduction on the ConOps and how we're planning to operate Squad in space is to quickly kind of jump over regulatory hurdles of transmitting from the radio in space. We only operate the radio in a RX mode. And so how it's going to work is on a pass over our ground stations, Squad will be turned on. From our LoRa ground station, we will ping Squad with commands and various LoRa packets. That will then be the result of those commands, and the data from those packets can then be read over I2C by SALI's avionics stack, and then downlinked over their ham band to another ground station. And then we will post-process that data, the Squad team, to look for the performance, see if there's hardware issues, and then also study the LoRa channel performance and see how good our link is. So one of the great things about trying to get something ready for space is you get to do a lot of environmental testing that is cross-use, right? It both informs your space-bound hardware and it also informs your terrestrial hardware. And so through the squad validation and test program and regime, we did a lot of exhaustive and robust testing. The hardware by itself, not integrated with Sally, and then also integrated with Sally. That included environmental tests, multiple TVAC sessions of the hardware by itself, and then also integrated with Sally, and then vibration, both integrated and not integrated. And additionally, we'll go over some long-range field testing that we did to really try and study the sensitivity and the performance and integration of the LoRa transceiver on Squad. So Sally's interface is I2C. We interface through their Sally's payload interface board. We have a harness that has power supplied to us through a load switch, an I2C interface, and then some sideband signals. And so Squad's flight firmware will go and manage the LoRa radio, go and manage the temperature sensors, manage all the onboard hardware, and then provide a set of registers that are accessible over I2C to Sally. And it operates purely as a peripheral device on the bus, so Sally is acting kind of as our master to pull data from the hardware and supply it to us after the fact. Because of this interface, and one of the great things about this simple I2C interface is that we could easily validate that, not having Sally's full avionics hardware. And so up here you can see we had a Raspberry Pi connected to our Squad payload over I2C, also powered over USB to simulate kind of power cycling through the USB hub on the Raspberry Pi. And then we also had two quad devices, one acting as a nominal transmitter and one acting as an interferer transmitter to generate error packets and fully try and exhaust all the cases that are firmware functionally, or try and check the full functionality of our firmware, make sure that it operates both when we get nominal packet reception and then also when we get erroneous packet reception. So, as you're prone to do when you write firmware, you put in bugs. So we found a bug through that test system that we had in which there's certain types of errors that the Mac can signal for LoRa packets, and you have to go, once you receive a packet, you have to go and clear those error flags. We were not clearing all of them, and one of the error flags that showed up ended up being latched on a power cycle, right? So if I get an error packet that is erroneous in this specific way, that flag would get set. If you don't go and clear it, technically all the packets after it, erroneous or not, still could have that error in it, right? And so that was a bummer. The bigger bummer was that by the time we found that with our automated test system shown on the last slide, we were already integrated with Sally and didn't have the ability to go and reflash the hardware. And so our quick mitigation for that was to tell Sally's avionics stack and their firmware, hey, go read a different set of registers in our register space such that we can still operate with pretty high functionality, even though we found that issue. Okay, I should start running. Here, we also, great thing is we did TVAC testing. TVAC testing is great, especially in RF systems, is that there's, one of the big things is temperature differences between an RX and TX node. If there's a big differential, you might see a lot of demod errors, and so that is cross-use and super helpful both for our terrestrial system and verifying that, and then also our space-bound system. We didn't find any errors during that, and the system was performing very well across very big temperature differentials between a transmitter outside of a chamber and inside. We also put it on a vibe table. This is not as helpful. Space can actually be kinder from a vibe standpoint than humans are with electronics, and so, but we tested it prior to shake, we tested it after the shake, and saw no difference in performance, which was great to see. We built this automated distributed tester where past research that our team did here at Cal Poly showed that LoRa is really good, and it's really good at pulling signal out of the noise because it uses this spread spectrum modulation. One of the issues of that, though, is if you do confined lab environment testing, it's hard to completely decouple and prevent leakage. And so one of the things that we wanted to do was test this hardware at a long range to try and block that leakage path in our radio. And so we built this system where we took it outside, got about 8.3 miles of distance, and then we used a automated test system to sweep channel configurations on LoRa, and then we would change the attenuation as well and sweep the channel configurations again to kind of come from both sides of the link and try and figure out, okay, how sensitive is Squad really, right? How good is it actually integrated onto the hardware? Here's some closer pictures. We have the TX node, some fixed attenuators, and then the RX node. This was done in Colorado, which is great for LOS testing where you have the mountains and the plains. So if we look at all the data, and you kind of take an account, do your link budget accounting, you can kind of say, okay, where does it fail and where is it still succeeding? And you can kind of collapse in on, you're missing about X dB of performance, right? And what we're seeing from the difference between what we think Squad heard, the power it got of a packet, to where the channel setting was, where it was still demodulating properly, we're seeing about 6 to 9 dB of missing performance. And there might be stuff in the link budget, but in reality, it probably is pieces of the integration that are eating into that or adding more to the noise figure on your link budget that might be causing that delineation in performance. And so what that taught us is that, hey, we need to try and find more link margin, and we'll do that with our ground station, which Shami will detail further.
On the EE building. It has a PoE injector and a switch to provide power and networking, and we have a PC for mission control and testing. We have an interface box that integrates a Raspberry Pi Zero with a quad radio and a power amplifier, and we have a Yasu G5500 controller to steer our 915 megahertz Yagi antenna for transmission, and we've done an end-to-end test with the Sally ETU. From our ground station, we sent packets at 915 megahertz to the ETU in the CPCL room. And then the squad board was able to successfully receive all the packets and transmit them back to the CPCL ground station. And we verified that all the packets were correctly received and decoded. We also just got the squad payload turned on yesterday for a pass. We weren't able to successfully send packets and receive them, but we have verified that it's online, and we need to focus on pointing our antennas correctly so we can communicate with it.
All right, so this is our last chart. This is the get off the stage chart, and I'm at 1 minute, but we've had this multi-year relationship with OWL. That has resulted in a payload flying in space, so we're all very excited about that. Acquired quickly. We had to wait. I turned these charts in a week ago for the bus hops to detumble Sally on the hysteresis rides, and then we got turned on yesterday and had our first pass yesterday, and we kind of come to the conclusion that our antenna wasn't pointing in the right place to get the message through. But we will, right? So that's the next thing to work on. What's been really impressive to me about this project is that it's primarily been led and executed by students. And so that little font, that's our sponsor. There are 3 key personnel, me and a couple of other faculty members, and then everyone else, those are all students. And most of those students are undergraduates. We've had 4 graduate students who've worked on this project. 2 of them are standing here, 2 of them already graduated, and everyone else was an undergraduate who worked on this, and I think it was a really impressive program. So thanks for hearing our update. Okay. Do we have time for any questions? Okay, any questions? Yes?
I live in Colorado, so I came to school here, but I'm still a graduate student and work out in Colorado now, and so, yeah, live out there. So we took it out to a lot of mountaintops out there. That's the great thing about Colorado is it's plains, 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 mountains, and so you can get a lot of line of sight testing pretty nicely out in Colorado, so that's why we're out there, yeah.
Kevin's done everything except defend his thesis. So, so he went out, returned to Colorado and got a job out there, but has continued to support us. And this is his thesis project. Any other questions? All right, thank you very much.
All right, that concludes our session. We're going to resume again at 4 o'clock after the break. There's a couple of different activities happening. First, you can find the refreshments up on the second floor by the posters. We encourage you to go up to the second floor, get the refreshments, enjoy the posters. And there is a second lab tour that's departing from the registration booth at 3 p.m. for those of you who signed up for that. Otherwise, I'll see you upstairs, and I'll hopefully see you back here at 4 o'clock. Thank you.
Hello, everyone. Welcome back. We will be transitioning into our session 6, which is about mission operations, software, and autonomy. Our first speaker is Jose Velasco with Chasqui, and he will be discussing design and experimental evaluation of cross-Yagi antennas and optical upgrades for CubeSat ground stations.
Hello again. My name is Jose Velasco. I am with Chasqui Inc. in Pasadena, California. And today I'm going to be, yesterday I had a talk for some of you that were present. You might remember me. I talked about the optical communicator. Today I'm going to be talking about the ground stations that we are developing or trying to deploy globally. Specifically, we're going to focus on a ground station in Peru that is being implemented in an observatory in a city called Arequipa, Peru. And a couple of students there also designed a cross-Yagi antenna for that station. So I'll be presenting for them as well. They couldn't make it to the conference. So again, our company is Chasqui, and the professor and students are Pablo Yanyachi. He's a professor at University San Agustin in Peru, and the students are Miriam Quispe and Carlos Coragua. So the outline of the presentation include, I'll talk about the optical ground station network that we seek to deploy globally. Then I'll talk about the cross-Yagi antenna that the students developed over the past few months, and then I'll finalize with a couple of conclusions. So one of the main goals of Chasqui is to deploy a global network of optical ground stations. So our scheme is our approach is to go into observatories all over the world, and then observatories that are equipped with optical telescopes. And the goal is to team up with them, sign some kind of agreement through which we can use those telescopes, and then retrofit the telescopes so they are capable of connecting to satellites. So in that way, we can really use ground stations immediately. We already have terminals. We can retrofit them, so we don't have to wait a couple of years to get the permits, to get the funding, to build the sites, and then put the telescopes up to calibrate them. Everything will be there. So that is our approach to rapidly deploying this network. So we right now are looking at Peru and Spain. Also in California, we're looking at Table Mountain in Pasadena, right behind Pasadena. So that's another site we are looking at. In Australia, Canberra, we're also looking at that place. Other sites in Hawaii and others. But what I'm presenting today is the work that we're doing at Universidad Nacional San Agustin, UNSA. So that's a university in Peru. So this is kind of the network that we're trying to deploy. I mean, basically, you can see the 3 complexes, California, Peru, Spain, and you get the picture. We want to deploy not only the ground stations, but we want to deploy LEO satellites and satellites in GEO and create a network. So we're not only deploying the terminals, not only deploying the ground stations, we want to deploy the whole network, including space, air, ground, and then provide services, commercial services to the community. So that's our ultimate goal at Chasqui. So this picture kind of gives you an idea of that network. Now, more specifically, I mentioned GEO. So this is our goal. We want to put networks, ground networks on the ground. On the ground, you have ample space. So you can have large ground stations, 2 meters, 3 meters, 5 meter diameter ground stations, optical mirrors. We want to put satellites in GEO. It starts with 8, like you see there. 8 satellites equally spaced, 45 degrees apart, to create a GEO belt. And then we want to connect the satellites in GEO with the ground at 100 gigabits per second. And actually, we have a capability to go to a terabit per second. So that's kind of the goal. So it's a huge goal, as you can imagine. But we are going step by step now, developing the terminals that you saw yesterday. I don't know if you were able to attend my talk yesterday. But we are developing the terminals already. We are about to embark on developing the satellites, and then we're going to begin deploying them. In addition, in parallel, like you can see, we are setting up the ground stations as well. So this is some pictures of myself in Arequipa, Peru. This is the observatory in that city. And these are older telescopes, as you can see. The one on the left, the green with white, the green ring, that's a 90 centimeter telescope, and the one on the right is a 60 centimeter telescope. They work, they can point exactly at the point we want to point. And so what we are doing here, you can see that's in the back is Professor Yanyachi, that is the PI at that university. So we are retrofitting these telescopes so they can do laser cam, basically. And we actually signed a memorandum of understanding with Professor Yanyachi at that university to do so, exactly that. So with them, what we want to do is upgrade the telescopes, add these optical terminals, and also develop the terminals in Peru. So that's what we like to do everywhere we go. We can actually develop the technology there. Obviously, we have the patent on it, but at least we can train the students, involve professors, and then we get to use the ground stations. With the idea that eventually we can even have agreements to put our new ground stations on the same sites, because the sites are ideal. High altitude, 90% blue skies under the air, which are ideal for optical communications. So that is so I visited several times. This is one. This is another time I went. Actually, you can see my hand at the end of the telescope in the middle of the picture. I don't know if you can see that, but anyway, so we were retrofitting because these telescopes were designed to operate at 635 nanometers. So they have some shatters in the way in the optics. So we had to open them up very carefully, remove some of the components, do some calibration. And you can see on the right, actually, we're illuminating with a red laser. And you can see the output, that's the window on the right, foremost right. It's that, which shows the very good collimation and focusing of the beam. So this is ready, and so I'm going back in a few weeks to add one of the terminals I presented yesterday. So the idea is that if we have a satellite illuminate the telescope, our terminal will detect the direction of the incoming beam, which is azimuth and elevation. And then we send that information to these telescopes, and they point in that direction. So we can actually do the tracking. But the intelligence will be given by our terminals. And that is the detection, the pointing, acquisition, and tracking will be done by our terminal. And so that's what we plan to do everywhere. Just take our terminals, connect them to the optical telescopes, and then provide that PAT information to the telescope. Now, switching on, this is, again, we're going to focus a little bit on the VHF and UHF antennas the professor and students at UNSA developed over the past few months. So these antennas obviously are RF, working VHF 145 megahertz, and UHF about 430 megahertz. So the ratio is about 3 in frequency. So the goal is that, you know that when you have a satellite pointing to a JAG antenna, if the polarization, if the satellite typically has a linearly polarized antenna. If it radiates that signal to your antenna, if there is no proper alignment or polarization, you lose some power. And there's nothing you can do about it. That's just physics. But now if you have a circularly polarized antenna, meaning two sets of antennas collocated but perpendicular to each other, then you recover that, whatever you lose with a linearly polarized. So that was the motivation of this work, is to develop what they call a cross-jack antenna that can take and generate circularly polarized signals. And in that way, improve your SNR and maintain your link without having to worry about the polarization alignment. So you can see, so they had two antennas. One is the VHF on the left, is about, I saw it 3.5 meters long. It has 9 elements per plane, so it's 18 elements on the left. And the UHF is a little smaller because it's 2 times higher in frequency. It has 16 elements times 2, so 32 elements. It's about 3 meters long. So just to give you an idea of the size. And so this is actually a simulation HFSS. You can see the antennas there, you know the size now. And these are the patterns that they got, the radiation patterns. So just something to mention, on the left for VHF, the gain is about 11.3 dB, which is kind of typical. And on the right for UHF, the gain is about 15 dB, which is, again, very typical, similar to conventional antennas. So so they had a very good simulation going. And one of the key things, when you have two sets of antennas, and they're identical, like these cross-polarization jack antennas, you have to have you have to match the phase properly. Because in order to reproduce, say, if you are receiving the signal, now you have two sets of antennas receiving the same signal. You have to combine that signal properly. So it has to be a 90-degree phase shift between the two. So that's what this combiner does that. So I helped a little bit with this design at university, this specific design. So you can see on the right, you see antenna 1, antenna 2. So that's how the signals come. But you can see that antenna 2 has an extra piece, and that's the phasing stuff. That's what gives you the 90 degrees compensation. So we fine-tune that. And then at the outputs on the left, then you have the two signals combined properly, coherently. And then you improve your SNR in that way. So that was done by the students and the professor. They built it, and actually they built antennas. But before I go, you can actually buy these antennas. You can buy linearly polarized, and then cross antennas. But it kind of gives you an idea of the gains. You can see if you go from the top to down. Yeah, the gains vary from 12 to 16 dB. And the prices, you can see this in euros. So the students, the professor, what they want to do is build their own antennas for 1/3 of that price. Anyway, so that's the impetus and the desire. But actually, so they did a good job, and they can save some money. So these are the antennas, actually, you can see. So on the left is the VHF antenna. On the right is the UHF. And you can see the VHF antenna has about 9 elements on each plane, so it's a total of 18. On the right, it has 16 elements each, so it has 32 elements. And then they actually tested these antennas. They're still what I told them to do is that they need to get a radiation pattern, a measured radiation pattern. So they had to put it into an anechoic chamber. So what they are doing now. But what they've done is actually some measurements with an echo analyzer, just to look at the antennas work properly at the right frequencies. So you can see on the left, that's the S11 parameter. So you can get that kind of resonates at 146.6 megahertz on the left for the VHF. And on the right is 436, which are very close to the design frequencies. So they have that and assembled, tested, at least they got that testing done. And next, Let me see. Oh, okay, so what they did is they did some preliminary testing. So there's a satellite called the RS-44 satellite, that I think is Russian, that is in LEO. It's an elongated LEO orbit, and produces a beacon. Every 10 seconds, it sends a beacon saying, I am RS-44, in Morse code, actually. So that's why you see those bursts. I put those dotted, I don't know if you see those dots there. So that's actually the Morse code. It says, you know, R is dot, dash, dot. So the first pulse, and you see multiple pulses. So anyways, they were able to capture that beacon. Not only capture it, you can see they can track it with those antennas. So this is 433 megahertz. So this is the antenna, the two antennas, and I don't know if you see, there's a mast on top of the building behind. So this antenna is meant to be put on top of the mast. So it's up, like 10 feet up. So also what we want to do, we only have 1 minute left, but you see a building here, so we're gonna modify this building and make it a mission control center. So the end product will be this. So this is ChatGPT for you. But you can see the telescope on the left, the control center with an edge data center in the middle, and the UHF antenna. We also are considering adding an S-band antenna. But the cool thing of this is that the edge data center can collect information, process it, and provide it to the user in near real time. With that, I'm running out of time, so thank you for your attention, and do I have one question? One question. Thank you. Yes.
Thank you. On your optical links, I'm interested, what kind of data rates are you trying to achieve, and what kind of pointing accuracy do you need to close these links?
Yeah, so yeah, good. Data rates, minimum a gigabit per second, but we would like minimum. Okay. But we want to go to 100. We have the aperture, you know, with a 60 centimeter. Also in Spain, we have 2-meter apertures. So we could go actually to 100 gigabits per second from LEO, even from MEO. So GEO depends on how much power you have on board. And then the accuracy is, you need several tens of arc seconds. Yeah, yeah, yeah. Because our divergence is about 100 microradians. So in radians, you have to be within that, right? So you don't lose something in the few microradians. So again, yeah, a few millidegrees, let's call it. I'm switching, but anyways, but you get it.
Your satellite needs exquisite attitude control to hold that tight, right?
Yeah, yes, because you know, we can talk afterwards, but our system, our optical terminal has an array of detectors that allows you to actually control the pointing very accurately. So we are counting on that to compensate for that. Yeah. Okay, thank you. Okay. Okay, I'm sorry. We'll talk after. Okay, thank you. Thank you, guys.
Hi, everyone. I'm very glad to introduce Jane Lee from Yosei University, who will be speaking on the ground segment operations and on-orbit validations of the B1000 CubeSats.
Yeah. Hello, everyone. My name is Jane Lee from Yonsei University. And today I'm going to introduce our ground segment operation and on-orbit validation of the CubeSat named B1000. But before I move on to the main topic today, I would like to introduce Yonsei University and its CubeSat development first. Yonsei University started our CubeSat development in 2012 with a CubeSat named Carnival X. And in 2022, we developed a CubeSat named Miman, which we got the Minister's Award and is still operational. And in November last year, we developed 2 more CubeSats named Cosmic and B1000, and we are now currently operating those. And currently, we are also participating in developing 3 more CubeSats, which are Ulysses, B1012, and ST1SAT. So as you can see from the slide, Yonsei University is now focusing on developing the satellite, especially the satellite bus. However, to operate our satellite successfully on orbit, we always need the corresponding ground station. So today, I'm going to introduce the ground segment of Yonsei University. So our ground segment consists of 2 main parts, which are hardware and software. In case of the hardware, as we are using 2 different frequencies, we have 2 antennas for UHF and S-band. And also, to amplify the power signal, we have power amplifier, and to amplify the signal coming from the satellite, we have low noise amplifier. And to control the antenna, we have rotator and rotator controller, and for both frequencies, we have the transceivers for them. And ground station PC completes our whole hardware. And in case of our software, we developed many features for operating our satellite successfully. So the first thing will be satellite tracking and antenna control. And we can also send telecommand or receive telemetry from our satellite. And we can transfer large files through FTP, which is File Transfer Protocol. And we can also manage our parameters of the satellite by using our functions. And we can also do autonomous operation of our satellite. So as I mentioned before, as we have 2 frequencies, UHF and S, we have the separate hardware structure for each frequency. So this slide shows our UHF frequency hardware structure. So our UHF antenna and ground station PC is serially connected to each other with 2 separate lines. One is for controlling the antenna, so we have rotator and rotator controller. And the other is for signaling the signal, so we have RF switch box and the transceiver for them. And the reason why we are using switch box is that we have to switch between the receiver and the transmitter side. And in case of the S-band, as we are using S-band only for the downlink, it is kind of simple than UHF structure, but we do have rotator controller and transceiver for our S-band. So using those hardware, we also develop software too. And we are now using 2 key protocols for communicating with our satellite. And the first protocol we are using is Consolidative Committee for Space Data System, called as CCSDS. In original CCSDS, they define a complete multi-layer communication stack. However, for simplicity, in our system, we are using only a partial part of CCSDS, which are its packet structure and its error correction and detection strategy. So in our system, CCSDS enables the identification of the command type that we are using. So in the bottom side, you can see the example of our system. So left side demonstrates the ground station software, and the right side demonstrates the satellite's OBC. So if we send some telecommand to our OBC is gonna understand the command by predefined message ID and command code. And it's gonna reply to us, which satisfies our bidirectional communications. And the second protocol we are using is CubeSat Space Protocol called CSP. CSP is a lightweight network protocol designed by GOM Space. So if your device is not from the GOM Space, you can still use your device as a CSP device if you implement the library on it. So in our system, CSP enables direct communication between the ground station and the CSP devices, which is very powerful. So in our system, almost all devices is working as CSP nodes. So using those protocols, we are now communicating with our satellite successfully. And from now on, I want to highlight 2 key features of our ground station. So first feature I wanted to emphasize is tracking procedure. Flight dynamics and tracking. So the flight dynamics and tracking process divided into 6 parts. And looking at it step by step, first we have to load TLE data either from NORAD or from local storage. So in the right side of this slide, you can see our real example of user interface. And after that, we are now using SGP4 library to propagate our TLE. So as you can see, we are using the open loop orbit prediction, which makes our system simple and provides a sufficient tracking performance that is needed to LEO satellites. And we have to compute the satellite and observer relative geometry. And here we are now using a LMST-based coordinate conversion, which makes our system simple without introducing any unnecessary computational complexity. So on the right side, it is a computed past parameters of our user interface. That's the real example. And after that, we have to generate azimuth and elevation commands for our rotator. Here we are now using look angle prediction based on our operational heritage. It means that we are not using a current azimuth and elevation value for the rotator, but we are using 3 to 6 seconds ahead of its value to compensate for its rotator lag or some kind of external disturbances. And lastly, we apply Doppler correction using the range rate. And the next feature I want to highlight is our data transfer, which is called CSP-FTP, the file transfer protocol. It can be broken down into 5 steps, and looking at by step, in our FTP, our ground station always has to start its session. So in the right side, you can see our real operational log, which sends the file transfer into the OBC. And when satellite receives the FTP request, it's going to reply to us with the transfer status. And after that, missing data is identified and transmitted. So if you look at the log on the right side, it says it starts at 638 with a count of 11. It means that 638 packets were already transferred, and there are 11 packets to go. And when FTP ends, the satellite and the ground station is going to calculate the CRC, the checksum value, separately. And after they compare the calculated value, and if it matches well, it's going to close the FTP session. So using those hardware and software, we are now operating our CubeSat successfully. And today, I would like to introduce B1000 CubeSat we are now operating. B1000 CubeSat was co-developed by Yonsei University with the Space Lintech, which is the startup company in Korea. And Yonsei University was in charge of developing the satellite bus system plus the ground segment. And the Space Lintech was in charge of developing the payload. Our B1000 CubeSat was a 6U size CubeSat with 600 kilometers of altitude. And the primary mission of the B1000 was to conduct an experiment about protein crystallization. And the second mission of it was to observe the Earth. So from now on, I'm going to show you an operational results of our B1000 CubeSat. The first result is about flight dynamics and tracking performance. And in the left side, you can see that our past parameters are calculated. In the right side, it is the past parameters calculated from the GPDM, which is the open source program. And when compared to the open source program, we found out that our software is calculating the past parameters well. And this is the communication results we got from the satellite. And in the left side, you can see our bus beacon data we received from our satellite. And in the right side is a result of bidirectional communications. And this was the result of after we sent a certain command to our satellite. And this is what we uploaded by using our FTP. We had patched a payload app using our FTP, and we also uploaded the ADCS commissioning file using our FTP. And this was the downloaded data using our FTP. Picture on the top shows the received images of Earth, and picture on the bottom shows the ADCS commissioning result we got from the satellite. So in Yonsei University, we are now operating our satellite end-to-end from developing the satellite bus system to developing the satellite ground segment systems. We have validated that our ground station is working well by tracking performance or transferring the file or conducting a bidirectional communication. As Yonsei University is open to any kind of collaboration, so please feel free to contact us by those emails, and thank you for listening today. Any questions? Yep.
Do you encrypt your command uplink?
Sorry, say that again?
Do you encrypt your command uplink? Do you have any encryption on it, AES-256 or anything like that?
We are using the protocols for our uplink command. Are you talking about that? Is that right?
So some operators encrypt their command uplink
Mhm.
so that somebody else can't take control of their vehicle. So something to consider for future work.
Oh, yeah, we should consider that as our future work. Yeah?
So the FTP, you have an FTP server
Mhm.
on the CubeSat. So do you use the FTP server as a repository for the sensor data, or you just use it for testing uplink, downlink, FTP?
For now, we are using our FTP for uplink and downlink data transfer, but later on, we might use it for like different purposes.
So the camera, when it takes a picture,
Mhm.
creates an FTP file, and a file in the FTP, and then you bring down that image as a FTP
Yeah.
via the FTP protocol?
Yeah, FTP is kind of an application that is, yeah, on OBC. So yeah, every file can be transferred through FTP.
Can somebody else upload something and download?
Yeah, actually, we are modulating our signal by RF signals, so I don't think it's possible.
Oh yeah, I understand. You need an RF link, but the FTP server is public or is only for you? I mean, somebody else can upload something on your FTP server and download?
Oh, yeah, I think we should think of it more.
Thank you.
Any more questions? Okay, thank you for listening.
All right, please welcome our next speakers, Henry Danielson and Clara Davis from Cal Poly SLO, discussing the NASA F Prime and AMSAT integration.
All right. Welcome, everybody. Very excited and honored to be here today. My name is Henry, and this is Clara, as this nice person has welcomed us. It's very cool to be up here on stage, and thank all of you for coming today. I'm going to let Clara start it off today for us, and then I'm going to come talk a little bit about cybersecurity and space and satellites. Clara?
Hello again. So I'd like to start off with explaining what is a CubeSat sim in particular. It's an educational project by AMSAT for like schools and hands-on learning. It's a low-cost satellite emulator. It has solar panels, batteries, radio telemetry, and it's all 3D printed. The custom boards are also all open source if you want to either buy them or get them manufactured. And it also runs on a Raspberry Pi 02 and a Raspberry Pi Pico microcontrollers, both of which are very common off-the-shelf components. The rechargeable batteries, all the telemetry sensors, and a Pi camera that you could imagine. And it is, again, fully open source, which makes it very useful for educational purposes. So why did we choose CubeSat Sim to port F Prime onto? Well, it's all about the learn by doing philosophy here at Cal Poly. We want people to have a platform to make mistakes and debug and understand all the components like power and communication that go into building a satellite before they, potentially move on to projects where satellites will actually go into space. And then, of course, being us, we research cybersecurity, so we want people to know cybersecurity principles as well and how they apply to space. So how is it used? Obviously educational programs, but the power of this here is the hands-on component. There's certainly something to be said about building the components yourself and watching that code run and seeing it work that really sticks in someone's mind compared to just buying something off the shelf. And of course, why that matters, all you need is curiosity, willingness to learn, and a soldering iron if you want to get started with this project. So what's next? How are we modifying this? I've been working on porting NASA JPL's F Prime flight software onto this hardware. Of course, Henry has the cool hat right now. So we, again, want it to be an educational resource for potential demonstrations and workshops. It was partially spurred on by some friends teaching a satellite hacking course at DEF CON and Black Hat, which are two very popular cybersecurity conferences. So we want to eventually have it as a live cybersecurity testing tool for hacking courses. So why F Prime? It's been used on real missions. It's like an industry component. It has actually flown on Mars and as a lunar flashlight CubeSat, which is pretty cool. Again, its modularity allows it to adapt to pretty much any project, and it's ideal for this purpose because it's also open source, and the more we have open source software on open source hardware, and then we blend the open source community of F Prime and AMSAT together, I think there will be some great cross-conversation between the two that will make a lot of difference and spur on more learning. So here is the setup. You can see the downlink portion, the uplink portion is facilitated through a HackRF, just on my laptop, and with GNU radio and then Direwolf, which is a APRS packet like encoder, decoder, that is running on board the ground station, which is just my laptop for the time being, and the CubeSat Sim. The ground station was also utilized RTL SDR, for radio ground station testing and verification. And then I also had to put together a cross-compilation environment because I'm compiling for ARM, like 32-bit ARM, and I am on 64-bit Intel. And it's also interesting because the Pi Pico is a different architecture than the Pi 0, and I'm having to do all that for the sensor work. So a little bit more about the architecture. I've been working on the downlink portion, which is part of the USB sound card, AMSAT deframer, and a ground station plugin that will interact with GNU radio and everything having to do with the HackRF. And then Madison Wright, who was an intern at JPL, she worked on the uplink portion with the radio bridge AMSAT framer, and then also some code for the Raspberry Pi camera that's on board. And then another student here named Sahil, he worked on like the HackRF and radio toolchain because radio was a huge important component, and as a computer science background, I was struggling with it, so we had to call in some help. But that's okay, he did great. So a little more about the architecture. For the uplink portion, the direwolf instance running on my laptop will send out a test packet, and then that will go into the USB sound card, which will it'll deal with direwolf's KISS framework, and then take the AX25 frame and send that to the deframer, which will then deframe it, obviously, and then validate it before sending it to F-Prime's built-in command dispatch code. And then, of course, for the downlink, it's essentially the other way around, right? We'll send a test command through the ground station into the framer that'll wrap it in AX25 frames, and then the radio bridge transmits that. And so as of right now, we do have uplink working from the HackRF, from direwolf on the CubeSat sim. It is able to pick up that telemetry. I'm still working on the other portion of the downlink, which is getting the ground station to actually command the HackRF. It's just that's less of the F-Prime components and more just an extra plug-in layer on top. But of course, TCP is operational. That's just built in. And then, yeah, again, I'm still working on the end-to-end and fully integrating the RF command dispatch. So I'll pass it off to Henry right now.
Thank you. Thank you, Clara. Again, amazing work this young lady's been doing, and I'm very honored to have been working with her, and very excited that we're going to be able to give AMSAT, CubeSat Sim, and F-Prime a way to teach others about compromising CubeSats. So I want to talk a little bit about hacking satellites and compromising. First of all, you all know that there's probably not a lot of encryption going on with your CubeSats, and I want to raise that bar and start thinking about that. And space cybersecurity is of the utmost importance currently to our reliance on satellite networks, space-based systems, and they continue to grow very rapidly. And these vital assets, again, as you know, are crucial functions such as exploration, communications, navigation, weather forecasting, and our national security. And in securing the security of these space assets is essential to safeguard against potential attacks that could disrupt critical services or our critical infrastructure. We don't want to compromise our sensitive data that is out there, or even pose threats to our current national security. Amazing story. I think it's almost been 4 months, I could be wrong, but UC San Diego used an $800 worth of consumer-grade equipment, off-the-shelf satellite receiver, located on their campus, the rooftop of UCSD. And the researchers spent 3 years, from 22 to about 25, scanning 39 geostationary satellites. OMG, the findings. The intercepted data, and nearly half of the satellites were transmitting sensitive data without the word encryption. The data exposed that they were allowed to discuss were T-Mobile user call and text, in-flight Wi-Fi activity, Mexican military police communication, and data from US industrial control systems and our military vessels. We want to talk and think from now on about secure by design. We need cybersecurity professionals in the room with us. It's critical. And the CubeSats, there is some limitations, power. The word encryption requires a lot of power, and we're trying to figure that out. So one of the things that I also wanted to talk about was some of the current cyber attacks. In 22, a cyber attack that all of us should be aware of was a cyber attack targeted to Viasat, the internet terminals in Ukraine and across Europe. This attack aimed to disrupt critical communications or comms infrastructure by wiping the firmware from the targeted modems. Rendering them effective, effectively unusable. So one of the nice, cool visuals I got up here is it starts out with the internet, goes to the ground, comes to in orbit, and then the end user. They were then able to go to the link, the user segment, and then finally do some bad stuff. I do think that I want to tell you one more thing about what it's like to work in a cybersecurity professional environment, and JPL is leading that charge. They did a wonderful thing out there by doing a test on their F-prime. And what's cool about that is they did an adversarial assessment and looking exactly at how to protect and make sure that their software was amazing. So this paper that they wrote here, adversarial assessment of the F-prime flight, they did findings and recommendations to share and show how they found stuff and how to mitigate them or how to fix them. I do want to say, number one, thanks for Alan Johnston's response and support, the AMSAT CubeSat Sim Wizard, I like to call him. I also want to give thanks and love to JPL Stephen, I'll call him, Cal Poly Cybersecurity Institute, the Noyes School of Applied Computing, Dr. John Bellardo, who you've seen and running this for many, many years, and also the PolySat team has been very kind to us, Dr. Bruce DeBrule, and again, my last word, secure by design is paramount. Thanks again. My name is Henry Danielson again. This is Clara. If you have any questions for us or seeing us around, can we take a pic over here? And again, thank you for your kindness. Is there any questions? Yes? Yes, there is ways to do that. Yes, sir. So find me. Yes? Thank you. All right, let me grab our friend. And thank you for your kindness, everyone. Have a great day.
I'm proud to present Alan Young from Georgia Tech. He will be speaking on GPDM mission operations development and blending different operation techniques.
All right. Good afternoon, everybody. My name is Alan Young. Today we're going to talk about the green propulsion dual mode mission operations development, how we blend both JPL and JSC operation techniques for our mission operations system. Ooh, okay. Cool. We're going to look at our mission overview. I don't know what's happening with these slides, but first thing we're going to talk about green propulsion dual mode. So green propulsion dual mode, we are a 6Q CubeSat that is operated and managed by the NASA Marshall Space Flight Center, and we will be operated and integrated by Georgia Tech. So we are a 6Q CubeSat that will operate in sun-synchronous orbit, in low Earth orbit, that was planned for launch no earlier than this fall, upcoming fall. So we are a primary technology demonstration mission. So our primary objective is to demonstrate the Ascent green propellant, which is a much less toxic propellant, monopropellant than hydrazine. Our additional primary objective is to demonstrate a dual mode propulsion system. We have on board both a chemical monopropellant system and an electric propulsion system, which will allow us to use both low thrust and high thrust capabilities. Our secondary objectives are to demonstrate the electrospray reservoir filling, integration of the spacecraft bus, which we are developing at Georgia Tech, and integration of the prop system being developed by Rubicon Space Systems and MIT, and integrating those two together at Georgia Tech, and fostering spaceflight operations capabilities at Georgia Tech in and of itself. Our concept of operations for GPDM is that we will do a series of orbital raising and orbital lowering maneuvers in which we will launch to a 590-kilometer sun-synchronous orbit on a Falcon 9 this upcoming fall. And utilizing both the chemical propulsion system and electrospray propulsion system, we can demonstrate the ability to utilize both systems to adjust our orbital altitude. The mission chain for Georgia Tech's operations will start with us as the Mission Operations Center. We will provide operations and scientific data to NASA Marshall, and they have been providing us project management and engineering support. Our science team is both MIT and Rubicon Space Systems, both of them providing us the propulsion system that we are utilizing as our primary payload. And we utilize KSAT Lite as our NASA Near Space Network contractor to provide us uplink and downlink capabilities for our spacecraft around the world. Okay, let's look at our GT operations heritage. You have to bear with me as seems like the bold part of my words seem to not be working. But Georgia Tech's spaceflight operations heritage comes from our operations of interplanetary mission. While we've operated multiple spacecraft in the past, our most recent mission was the Lunar Flashlight mission. And this Lunar Flashlight mission was utilizing the DSN in conjunction with JPL. So our flight control team for mission operations for Lunar Flashlight utilized a 3-person flight control team. The flight director, which is our primary authority, our ACE, which is our spacecraft link engineer, who was setting our commands, and our telemetry engineer, which is actually providing the telemetry data analysis that we need. In the background of all of that, we actually have multiple subject matter experts from NASA JPL and NASA Marshall that allowed us to actually analyze all the data that was coming down for our spacecraft. So utilizing for our operations for JPL and Lunar Flashlight, we adapted a bunch of JPL processes into our operations. Firstly, we decided to divide our tactical and strategic operations such that we allow distinct phases, tactical context, where we are actually in contact with the spacecraft, and strategic planning, which is in between those contexts. We utilize sign, countersign procedure checklists, where every single step, every single action performed by the ACE on console is required to be countersigned by the flight director in order to perform that action. By nature of us using the DSN, we actually were able to utilize a joystick command capability for the spacecraft itself, which means that we could actually send a single command up to the spacecraft, verify that it actually performed the command that we wanted to do, and then send the next command, which is kind of an exceptional quality that we utilized in this particular mission. Our flight director for Lunar Flashlight was our primary systems expert, which means that they were the ones making decisions and recommendations depending on how their knowledge of the system itself, which is slightly different than how you may expect other flight control teams to work. We utilize a testbed for activity and sequence validation and verification. And we staffed our engineers as operators for our spacecraft, which is a little bit different than the way JSC does it, which I will explain in a little bit. So there's some lessons learned that we have from Lunar Flashlight. The first thing that we did was that there was a bunch of information siloing due to our small team size. So we actually had the issue where only one person knew the knowledge necessary for a specific subsystem. Additionally, we lost critical software development skill sets as students graduated in the operations team, which severely hampered our ability to fix and update our mission operations system going forward. Furthermore, we had limited strategic operations simulation and training pre-mission, which actually ended up hampering us when we end up in our contingency operations, which goes to the 4th point. We had a high workload during the perpetual contingency operations for Lunar Flashlight, since the satellite was basically operating in a degraded propulsion stance the entire mission. So how do we fix that? What did we do to fix that on GPDM? First thing, we increased our team size. And secondly, I specifically hired non-aerospace and aerospace majors with software development skills to supplement our mission operations team to develop our mission operations system and ground data system. Furthermore, I expanded our strategic operations roles to have distinct roles and responsibilities and increased our pre-mission strategic operations training to allow us to actually simulate the ability for us to plan our specific increment missions. And lastly, we developed a robust anomaly response plan this time, and also anomaly scenario training to allow us to train for known scenarios that we believe are likely to happen on the mission. So, I talked about some JPL techniques that we've done for our mission in the past, but Georgia Tech operations for GPDM comes from both JPL and also my experience as an intern at the NASA Johnson Space Center. So I've been an intern at NASA Johnson Space Center for multiple times working ISS operations for visiting vehicles. And so I wanted to bring in some of those techniques to allow us to more effectively operate in low Earth orbit, which is kind of a different environment than we've been used to as of late. So what that means for us is that there are some new challenges for operating in LEO. Firstly, instead of our 4-hour-long contacts with the DSN, we now move to our 8-minute-long contacts with our NSN ground stations. Furthermore, in contingency operations, we, instead of having persistent DSN capability, if we were to declare a spacecraft emergency, because DSN has 360-degree coverage on Earth, we now have limited coverage and capabilities with our NSN ground stations. Furthermore, like I said before, we had joystick command capability for Lunar Flashlight. We no longer have the capability because we are moving from our lengthy ground-in-the-loop telemetry verification to our limited ground-in-the-loop verification by nature of our reduced time contacts. So we have to rely on our onboard autonomy much more to account for our critical activities, such as maneuvers. Lastly, very different than interplanetary operations, where the pointing for the sun and our antennas tend to be a little more favorable. We actually have a bunch of different trade-offs in our pointing requirements for our power, our GPS, our comm, and for maneuvers. So what are some adaptations we can use from JSC to assist us in LEO operations? Firstly, each flight controller that we have in our tactical flight control team and our strategic flight control team will be a system expert. So they are able to facilitate and make recommendations to the flight director to solve any problems that we encounter during operations. Secondly, we have predefined go-no-go points, which is slightly different than what we've done in the past with the sign, countersign checklist. So with predefined go-no-go points, we can allow the ACE to get to a predefined go-no-go point, get a go from the flight director, and then execute the rest of the procedure without having to verify back with the flight director for every single step. We developed an entire strategic flight control team, which will allow us to have specific defined roles and responsibilities and role division during the strategic planning phase of our mission, which will allow us to better facilitate activity development. We have a defined strategic planning increment phase. So at JSC, we utilize in the increment system, where a new increment happens every single time a Soyuz crew goes up to the station. So for us, we decided to bring that down to a smaller stage, smaller time scale. We're going to be operating in 2-week increments. Additionally, we have generalized standard operating procedures now instead of our specific activity-unique procedures that we did in previous operations, where we can have a specific, where we have a generalized procedure to utilize for multiple activities at the same time of the same type, rather than specific activities that were unique to that particular contact. Additionally, we modularized our mission operations system and our mission operations system tools to allow us to actually make building blocks of different activities as we go along for the mission to further assist our capabilities. So this comes to our GPDM mission operations and how our team actually is facilitated. So this is the hierarchy that we have, in which you can see that there are multiple temporary and permanent roles for both the strategic side and the tactical side, as well as our subject matter experts, which are staffed by both our undergraduate and graduate operators. So our tactical flight control team is as follows. So we have 2 permanent tactical flight controllers, our flight director and our ACE. And we also have temporary flight controllers that we can call in case of high workload contacts. So both the tactical MDA and our tactical nav officer, as well as any SMEs that we want to have on the console at the same time. For our strategic flight control team, we have 6 new roles that we have now defined, and they each have a different responsibility that is required of us when we need to give proper information to whether that be Marshall, whether that being Kara, or any other stakeholder in our mission. All right, let's look at our mission operations approach. So we're operating in 2-week increments. What that means is that during the strategic planning, tactical planning phase of the first increment, the strategic planning phase will start for the next increment. So for increment 1 tactical phase, increment 2 strategic phase will start. For example, this will be at MET L+0, which means that during the week of launch. So strategic planning means that increment 2 will begin their activity development for the next week of tactical activities. So for example, our nav officer will do the trajectory planning, our ops planner will do their staffing and contact availability, our test engineer will verify our sequences, our MDA will do their health analysis, and our increment flight director will be managing all of that planning process. In the meantime, our increment 1 team will be performing their tactical activities, which means that we're going to keep our flight director and ACE on console We endeavor to keep them as same-day teams, meaning that the same flight director and ace will operate on the same day, which will allow us to actually schedule our contacts to match the schedules of our flight controllers, which is a huge boon when it comes to student operations. And then we always have on call our SMEs and any other tactical flight controllers that we need. For the timeline, for strategic planning, we will start, for example, if increment 3s in their strategic planning phase. They will start with the initial planning meeting. They'll go into activity development. They will have a midweek meeting in which the increment 2 team will be able to debrief any anomalies that may have occurred during the week. Increment 2 will then be able to fully debrief their increments of activities to increment 3, and that will end with the strategic planning committee where we will stamp the increment plan for increment 3. This is a small spreadsheet or diagram of our certification process as well, something that we've brought on for GPDM, where we start with lectures for our mission operators. We will then move into some nominal simulation practice, and then move on to specific nominal and off-nominal tactical and strategic sims. Repeat it for each console, which will finally allow us to have our increment gen sim, which is a full 2-week simulation of activities, which will allow us to prepare as much as possible for any anomalous scenario that we may encounter on board. All in all, this allows GPDM and us to this allows GPDM to be resilient to anomaly conditions and scenarios when we're on orbit. Thank you very much. Yes.
So I'm trying to cram a few questions here. Great talk. Trying to get them all out there. Are you considering collision avoidance? You are measuring the effectiveness of the propulsion based on its impact on the orbit. So how are you getting a new orbit determination? And then finally, it looks like your 3 axis stabilized. You have wheels. Can you use propulsion in double minimums rather than changing your orbit?
Yeah, so the questions were a couple questions, so I'll touch one at a time. So firstly, about the wheels. So the question was, are we using 3-axis stabilization? Yes, we have an Exact 50 on board, which has a 3-axis reaction wheel assembly. We also have magnet torquers in that, so we actually utilize magnet torquers for our desaturation of those wheels. We could. But since the propulsion system is the demonstration of this, is the actual science that we are doing, we've elected to utilize magnet torquers, since we are also in LEO, which actually helps us passively desaturate. And the other question was, how are we doing collision avoidance with our multiple maneuvers? And how we're doing orbital determination. So we actually have our own in-house orbital determination software that's being written by our navigation team, and they will be providing the trajectory plan and our own TLE to CARA for collision avoidance. Right now, the plan is 3 times per day.
You have a beacon. You're going to get R&R dot turn something around?
We actually utilize, so we have a GPS antenna on board. So we can actually utilize our GPS position, and we'll downlink it, we'll filter it on the ground, we throw it through our supercomputer, and then we can uplink that package to CARA for collision avoidance. Mm-hmm. Other questions? All right, cool. Thank you very much.
Next, we have Bob McElrath from Dyson Labs talking about secure tasking through inter-satellite relay.
Hi guys, here to talk about cryptography really. Some of the previous talks about cryptography from you guys, thank you very much, were absolutely terrifying. Perhaps you guys should encrypt your connections. But here I'm going to tell you about some of the cryptography you have in your pocket that is not being used for satellite communications and probably should be. So the kind of big picture here is I want to build a system where I can order services from a satellite, right? Now, there's a couple problems with this. If I call up an operator and say, hey, I want to do this thing, operator A has to call operator B uplinks command, then they have to wait for another orbital pass until they hit their their command uplink window, and they have to wait another orbital pass to get over the target you want to take a picture of. And this takes hours to days, right? Let's say you live in California and there's a wildfire situation and you need to take a picture of the fire front, and you need it quickly because they move fast. You need to get people out of harm's way and get the firefighters in the right position. This might be something you didn't know you needed 5 minutes ago, but I want to order that service. How would I do that, right? You can't do that today. So what I want to propose here is two protocols, one of which essentially relays a command to a satellite, and the other is the way to relay. One is similar to OAuth, if you're familiar with that, and the other is similar to TLS, which are two protocols you have in your pocket already, but the space industry is very behind on this. So, you know, what you have in your pocket is SSL TLS, right? You go to a website, HTTPS website, you go to your bank website. This is what's being used, and we've been using it for a long time. The two servers establish an encrypted link. In the process, they establish a ephemeral key, which they encrypt the communications with. The whole point of this is that if the keys are compromised, the communication traffic is not compromised if it's recorded. We could be doing this with satellites as well. So we're proposing two protocols here. SISL, which stands for Secure Intersatellite Links, and the second is SCRAP, which stands for Secure Command, Routing, and Authorization Protocol. Any two satellites with compatible radios could be passing messages between each other to quickly relay a command. If one has a downlink and happens to have another satellite nearby who doesn't have a downlink, he could relay that over his RF link to the satellite in a close pass. That's basically the picture. If you're familiar with any of the kind of technologies that we have on the internet today, we have HTTPS, which every single website uses that. We've decided that's the standard. The standards in satellite communications really were developed during the Cold War when encryption was illegal. But we really need to move past that. We've already accepted all of these things in our pockets, right? So the first protocol, so the SCRAP protocol is similar to OAuth. If you've ever gone to a website and it says log in with Google, you push that button, they go to Google. Google signs what's called a token, which says this person has an account at Google, right? And it comes back to the original website, and they accept that token because Google signed it and lets you log in. SCRAP is a method of doing the same thing where the person who signs that token is the operator, saying you as a satellite are authorized to perform this action. The second is SISL. Now that is the way you get the message to the satellite. And the idea here is that we want to use RF to relay between satellites. But we want to do it in such a way that we don't interfere with anybody else. Because this is not there is really no kind of radio intersatellite links authorized by anybody in space right now. So what we're going to do is use spread spectrum RF. If you have a Bluetooth headset or AirPods in your pocket, they do 5 of the 6 things I'm going to propose here for SISL. So there are a couple of existing standards. Ours is basically going to be based off Proximity 1. This is a CCSDS standard that was used for the Mars rovers. Basically, the orbiter goes around and sends out a hail. It says, I'm here, upload your data. The guy on the ground says, I'm here, I'm going to upload my data. That's basically, it's a hailing protocol. But it has no encryption whatsoever. I mean, nobody was expecting anybody to intercept communications on Mars. CCSDS SDLS, which apparently some people are not using and should, is kind of a 60s/70s idea of cryptography. We have a single symmetric key, and you really hope it doesn't get compromised. But if it does, everything is gone. Everything can be recorded, everything can be intercepted. TLS is what your web browser uses today. It's certainly a step above. There are certain reasons why it's not quite appropriate for satellites. We're going to propose for SISL to use X3DH, which is triple Diffie-Hellman. This basically allows you in 2 messages to establish an encrypted communication channel with forward secrecy, so that if it's recorded, you still can't decrypt the data anytime in the future. We are doing a number of things here to hide the caller identity. We're using spread spectrum, we're using ephemeral keys. The initial motivation for this was actually not cryptography. It was, I want to stay below the noise floor of everybody else, because I want to relay messages in a way that doesn't interfere with anybody else. If I'm relaying a message to another satellite in the S-band or X-band, and there's somebody above me who's talking to his ground station, I don't want to interfere with him. He's going to interfere with me, that's okay. We're going to use forward error correction to correct that, but I don't want to interfere with him. And the long-term idea here is to test this and be able to prove that it doesn't interfere and have a way to actually relay commands between satellites. Diffie-Hellman key agreement, this is not a cryptography audience. I'm probably going to snow everybody with cryptography here, and I apologize for that. Basically, you have a static key. You have the satellite has a static key with which it uses to establish a new key, and that new key is used to encrypt the communications going forward. So these are the two messages going back and forth in the SISL protocol. You send a hail. The hail itself uses spread spectrum with a public spreading code. So everybody knows what the spreading code is. Everybody can see the hail. This is required if you want anybody to receive your hail, because they need to know what to look for. And we're basically hiding in the noise when we do this. And so I need to know how to pick that out. The responder then sends back an ACK, which has his own piece of the Diffie-Hellman agreement, which then both sides have all the information they need to communicate further in a completely encrypted way. They also authenticate each other in the process because they know the keys being used. So this is, in military terms, an LPI, LPD, low probability of intercept or detection method. If you were to just use a normal broadcast, you'd see something like on the left, where you have, of course, a peaked frequency at the frequency you're broadcast at. On the right, this is noise, right? So we can get about 30 dB of amplification by doing the right signal processing and doing the right spread spectrum techniques. In particular, DSSS, which is a direct sequence spread spectrum. The responder basically listens and tries to decrypt everything he hears. If he manages to decrypt it, because what he's gotten out of the noise was cryptography, he can decrypt it. If he can't decrypt it, he didn't get the message correctly. So the second piece is to add forward error correction, right? So some of the data I receive is going to be stomped on for various reasons or just didn't pick it out of the noise well enough. And so we need a way to be able to handle that. So if there's interference, you'll get the right frame there, so the sender is sending the same message over and over again, but he's sending it with a different rotation each time. And so I collect as many of those as I can, and when I have enough of them, I can reconstruct the message. So the sender just keeps sending at the noise floor, keeps sending the same message over and over again, and I keep trying to decrypt it until I can. And once I can, I respond, and I do the same thing in the response, right? I keep sending at the noise floor until he can get enough messages. This is a very, very slow method of communication. The idea is to communicate a order, so a command order. So the satellite says, all right, please take a picture of these coordinates, at this timestamp, and this is a couple kilobytes of data. There's been a lot of churn in this protocol in the last few days, actually. So we did a hackathon last weekend and implemented this for the first time and tested it using HackRF. Appreciated your HackRF radio demo. We basically did the exact same thing. I have modified the protocol in a number of different ways recently because of patents. Turns out a lot of these forward error correcting things are patented. Don't patent stuff, guys, please. So the scrap protocol. So this is your authorization token, right? So this is what the satellite receives that says, you are authorized to do this, right? So on the left is basically a key value list of things. It is what you're supposed to do. Take an image, take some electron density measurement, take some whatever instrument you've got aboard. If somebody wants it, they say, I want that, and it tells you what the instrument is. So the operator signs this off network. In other words, we construct the scrap packet on the ground. We are going to route it up to a satellite. Somebody has an uplink, and we're trying to do this quickly, right? So who's overhead now? Who has an uplink? And who's nearby that we can relay to? So this all happens on the ground. We know the TLEs of the satellites on the ground. We know their radio capabilities. Part of the reason I'm here is I want to talk to people about what the radio capabilities are, because ultimately we want to do this in the S-band and X-band. But we're dependent upon side lobes of your antenna to do that, unless people really want to point, which is another discussion, but you could point at another satellite. When we construct this task packet, we go to each operator. The operator runs a little API, and the operator signs the message that says, you are authorized to do this. And the operator has a choice. Operator can say, okay, I'm busy, I'm taking scientific data, I don't have time for this, whatever, I'm not going to authorize that. But once we collect all that, we put that all into a packet and send it up, and then the satellites relay it from there. The protocol flow goes like this. So that's what I just said at the top. We construct the scrap packet on the ground. We obtain each of the tokens from each of the operators. Now this can be tied to payment as well. There are kind of two order n squared problems to solve here. There's inter-operator coordination. There are jurisdictional issues with that. There are legal agreements to be signed. This is all very complicated, and it's order n squared problem. I have n operators, right? And if each of them has to have an agreement with all n other operators, this scales very poorly. Humans invented marketplaces. So the idea is that this is supposed to be a farmer's market, right? I'm just going to go buy an apple, and the apple seller doesn't have to know anything about the orange seller who's next door, right? This is why humans built marketplaces in the first place. So we uplink the scrap packet on the left. The sizzle then transfers that to satellite B. In the process, the receiving satellite sends back an acknowledgement. In the acknowledgement is essentially a hash of data that satellite A couldn't obtain. So satellite B decrypts his portion. This is onion routing, if anybody's familiar with that. Satellite B decrypts his portion and sends back an acknowledgement to satellite A. This is called an adapter signature. So using that piece of data that they receive from sending it to the next hop in the link, he receives a piece of data back. This can be tied to payment on Bitcoin. If we eventually want to have autonomous satellites doing autonomous interesting things, everything they do is digital, we have to have a form of digital money they could pay each other with for services. And at the end of that, each satellite has their own adapter signature, and they hold on to that until they get to their next ground pass, and they pass it back to their operator. And with that adapter signature, the operator can then claim the funds that the customer ultimately paid. This uses something called a point time lock contract. It's a way of taking a signature. Basically, in certain signature schemes, you can add a constant to your public key and then perform a similar transformation and add another constant to your signature, so that if, you can't do this unless you have the private key, unless you're the person authorized to do this. But this allows you to bind payment to execution. This is one of the only ways I know to do this. I think it's very cool. Most of the time when you go to the store, you buy something, there's this exchange problem where if I'm trying to buy shoes, I give you the money, and you run off with both the shoes and the money. If they give me the shoes first, I run off with both the shoes and the money. This isn't the only example I know of where you can actually have a payment execution binding. We can't tell if you took a picture of the right thing, or even if you took a picture at all, but we can tell if you relayed the message, which I think is kind of interesting. There's a plot of the link budget. Basically, we can get 30 dB out of all this extra signal processing. What this means is that this link closes about 500 kilometers in orbit with a 1-watt omnidirectional transmitter. And we're going to have to, with each operator, we'd have to discuss, okay, so what are your actual radio operational capabilities? What frequency band? What's the frequency band that the target can actually listen to? Is it full duplex, is it half duplex, et cetera? So I'm here to ask you guys to help with this. I want to try using this with real satellites. A lot of you guys are controlling your satellites with ham radio. We can do this over ham radio. We've tested it over all the 433 megahertz, 915 megahertz. We've also tested it in the Wi-Fi band, 2.4 gigahertz and 5 gigahertz, where there's a lot more noise and a lot more interference. So I'm hoping a few people here with CubeSats would be willing to try and do this. Long-term goal here is to prove that this is a non-interfering use case and get the ITU to explicitly say, you can do this is okay. There are a couple of documents we'd file here, one which would be an extension of the Proximity 1 protocol with a CCSDS. Another is an ITU filing to allow this use case. And it starts here. Let's try and do weird things with cryptography. All right, so I'll finish there. So these are two protocols. They're both open source. Our GitHub is a little bit messy. I'm sorry. We've been working on it very hard, but we'll refactor this soon to make it a little more clear. So Sizzle is the link layer communications, radio frequency. That's what we need ham radio for. Scrap is purely data packets. Both of these are Rust crates. They're very small. They don't use a lot of processing. You can easily run both of them on a Raspberry Pi, about 1 megabyte of RAM for each, and allow yourself to let other people control your satellite and pay you for it if you choose. So that's it. Yeah.
So really interesting talk. Getting at a lot of fundamentals here. A couple of thoughts. One is the big geo operators will sell you bandwidth. You can test this right now, run your spread spectrum for somebody's C, KU, X, whatever, and see what you get on the ground. I don't know that you need to fly this on a CubeSat to do it. My other thought was the commercial remote sensing operators there's currently a marketplace on the ground. You're going to have to do a lot of this on the ground anyway. And this is a lot of complexity because you either need a bespoke system that flies all your things, or you have to convince every operator to fly a receiver with your stuff in order to do it. Why not just, if you want to hide the customer and be kind of LPI, LPD, why not just set up some shell company or something and handle this all through the existing ground? You know, so go out to Planet, buy their data, go out to Umbra, buy their data, go out to Capella, buy their data, and the sellers don't have to know who the customer is because, you know, you're the middleman or somebody else's. What's compelling that drives you to the space-based architecture versus a ground-based architecture?
Because I'm a cryptography and space nerd.
Okay.
Yeah, you're completely right. I mean, Planet Labs, you can go buy imagery from them, but that's one company, right? The idea is to allow anybody to do this for any instrument, right? The companies see the value in this, right? But you know, it's still very hard to do cross-jurisdiction, cross-operator anything. So yeah, you could. I mean, it's more of kind of a business development thing to do all that. You could definitely do it.
Yeah, you could be the arbiter. You could hold the marketplace where you go to Umbra, you go to Planet, you'll go to Capricorn.
Not as interesting to me intellectually, I guess would be the answer. But yeah, you could do it. That's business development versus protocol and cryptography development, if you will. Yeah, go ahead.
So to implement these secure protocols, would it require for the onboard computer to have a secure domain into their process? No?
Not necessarily, no. So you need to upload keys to the computer or have it generate its own keys. And it has to, I mean, you're asking about secure enclaves, right? Or cryptographic operations. So some processors, for instance, have AES as a native instruction. We've chosen a couple protocols, Cha-Cha and Poly here, which are quite fast on a regular CPU. They're more resilient to single event upsets than AES because they're simpler. They're just XOR. And also, we just repeat the data. So if you get a bad computation, you're still going to be able to recover the data. As far as secure enclaves are really intended for physical protection of secrets. So you know, your iPhone has one, and that's intended so that if somebody got a hold of your iPhone and they wanted to extract the key material from it, it's a very difficult process. If someone wants to capture satellites to do this, that's a different realm of problem that we're not trying to solve here.
Wouldn't somebody be able to basically completely take over your software in the satellite, change your encryption software with their encryption software?
Not if you don't let them. I mean, if your command uplink was encrypted in the first place, which it should be, and you uploaded our software to it, this is just delegation. So it all comes back to your original encryption key. So if you have a single symmetric encryption that you're using to upload commands, this is delegation through that key. So you uploaded software that you authorized that uses keys in a slightly different way, but ultimately it comes down to your original encryption.
So basically your security is as strong as their encryption?
Yes. So yeah, if your satellite is currently completely unencrypted, anybody could upload this to your satellite. All right, thank you very much.
All right, thank you. That was the last talk of this session, and that's the end of our day for today. The breakfast will be available at 9 a.m. tomorrow, and we'll start the next round of talks at 10. So look forward to seeing you tomorrow morning, and I hope you enjoy your evening.